Hi, I'm Rob Ryder, and welcome to Volume 5 of Sporty's What You Should Know series. A part of flight training you'll find both interesting and different is flying at night. In just a moment, we'll take a brief night flight and cover the major aspects of night flying for pilots who've flown only during daylight. We'll introduce you to night vision, airport lighting, and give you some tips to help you with your night flying experience. You'll find that night flying is enjoyable, since the air will usually be calm and smooth. For your private certificate, you must have at least 3 hours of night dual instruction that includes a cross-country flight of over 100 nautical miles and 10 takeoffs and 10 full-stop landings. Night flying is considered to be an important phase in the complete training of a pilot. A pilot who becomes proficient in night flying gains valuable experience in case of an intended day flight that inadvertently extends into darkness. Remember that night flying is not really difficult, but it differs from daylight operations in that vision is restricted at night. You'll be challenged by the fact that you cannot see as well at night as during the day. However, there are techniques you can learn to enhance your night vision. For example, during the day, the best way to see something is by looking directly at it. But at night, dim objects are best seen by viewing them slightly off-center. This is due to the way the rods and cones in the retina of your eyes function. You'll practice what's called dark adaptation. This is simply avoiding bright white light before you fly to let your eyes adjust to the dark. This is similar to what you experience when entering a darkened theater or room. At first, you can hardly see, but within 4 or 5 minutes, objects start to become visible, and after 30 minutes, you are dark adapted. To help maintain dark adaptation, keep the cockpit and instrument lights adjusted to allow you to best see out of and inside the airplane. When over a brightly lighted area like a large city, turn up the instrument lighting. Eyes never function as effectively at night as during the day, but remember that if pilots learn to use dark adaptation techniques correctly, then night vision can be greatly improved. As part of a night pre-flight, you must make sure the airplane lighting system works. This includes checking the position or navigation lights, which are red for the left, or port wing tip, green for the right, or starboard wing tip, and white for the tail. Also check the anti-collision lights and the landing lights for proper operation. Next, check the instrument panel lights. If the airplane's electrical system has fuses, Federal Aviation regulations require a spare set, or 3 spares of each kind, to be on board. At night, it's recommended you have a flashlight in good operating condition on board as a backup in case of an electrical system problem. Keep it handy so you don't have to search around in a suddenly darkened cockpit. Some pilots use a small flashlight that can be carried in a shirt pocket or hung around the neck. As you and your instructor taxi out for your night orientation flight, the first thing you'll notice is how different the airport appears. Taxi slowly, especially if you are in a congested parking area. If the taxiway is lighted, it will have blue lights. As you taxi, you'll probably notice the airport beacon flashing alternately white and green. Alternating white and green flashes identify a lighted land airport for civilian use. Military airports have beacons that show 2 quick white flashes between green flashes. You might also notice some red lights. These mark buildings and obstructions in the airport area. Once in the run-up area, your instructor will probably have you turn off the landing lights to conserve electrical energy and to not ruin the night vision of other nearby pilots. Do a very thorough run-up using the checklist and be sure the generator or alternator is functioning. When ready to taxi for takeoff, turn on the landing and anti-collision lights. Ask for tower clearance or check the area carefully at non-towered airports. As you start to taxi towards the active runway, you'll notice that the runway threshold or end of the runway is marked with green lights. Some airports have runway threshold lights that are green on the approach side and red on the runway side to alert pilots on rollout from the opposite direction they are near the end of the runway. You may also see pulsating white strobe lights. These are runway end identifier lights. Runways are edge lighted with white lights. Once in the middle of the runway, check to ensure the heading indicator and runway headings are the same. Apply power smoothly and use the runway lights and the landing lights as a reference to help maintain direction. Check the heading indicator as you accelerate to the normal liftoff speed. Your first impression will be you're moving faster than usual. This is due to the lack of visual cues used in the day to help judge speed. At liftoff speed, apply back pressure to rotate to climb attitude. Use the same airspeeds you do during the day and adjust engine power as required for your airplane. Keep checking your heading indicator, attitude indicator, and vertical speed indicator as you climb. Look out for other air traffic as you climb. The location of navigation lights on aircraft is to help pilots see as well as determine the direction of other aircraft. For example, if you see an airplane's red light, you have the left wingtip in view, and it is passing from your right to your left and has the right of way. If you see a white light and a flashing red or white light, you are looking at the tail of an airplane. A green light indicates you are seeing an airplane's right wing, and it is moving from your left to your right, and you have the right of way. An aircraft displaying both red and green lights will be approaching head-on. An easy way to remember the right of way rules at night is, if you see green, you have the right of way. If you see red, you do not. You might have a question as to when to turn on navigation or position lights. Regulations specifically state that navigation lights must be on any time an airplane is taxiing or flying during the entire period from sunset to sunrise. They further state that from sunset to sunrise, an aircraft may not be parked or moved in a night flight operations area of an airport unless the aircraft is clearly illuminated, has lighted position lights, or is in an area which is marked by obstruction lights. Don't confuse sunset to sunrise to mean night. The period between sunset and sunrise is not necessarily all night, as defined by the regulations. Night is defined in the regulations as the time between the end of evening civil twilight and the beginning of morning civil twilight. By this definition, night begins sometime after sunset and ends sometime before sunrise. At night, it's important to know your position at all times when away from the airport. Use radio navigation backed up with dead reckoning. Ask for help from ATC if necessary. Remember that visual navigation landmarks simply cannot be seen at night out over dark country. Radio control of runway lighting is available at selected airports by keying the airplane's microphone on the appropriate frequency. It's recommended to click the microphone 7 times within 5 seconds to activate the highest intensity lights available. If the lights are adjustable, you may want to reduce their intensity by clicking the microphone an additional 5 times. Once activated, the runway lights remain illuminated for 15 minutes from the time of the most recent activation. As you approach an airport, pick out the threshold and runway lights for the active runway. Keep them in sight as you enter the pattern. Complete the pre-landing checklist. On final approach, check that the runway heading and the heading indicator agree. At night, you will find it's difficult to judge height and speed above the ground. Use the same approach airspeeds as in the day and make sure you're not low and slow or high and fast. On a low approach, the runway looks like this. A high approach looks like this. And on a proper approach flight path, this is what you should see. Use the landing lights to aid in determining when to start the flare for touchdown. Don't stare at the area lighted by the landing lights. Use the runway edge lights also for landing clues. Again, use power to control your descent to the runway and reduce it to idle at touchdown. Landing without landing lights is more difficult, but start to round out when you see the runway lights at the far end appear to rise above the airplane. Because of limited visibility at night, use caution and taxi slowly to your parking destination. Many runways use visual glide slope indicators to help pilots during landing approaches. VASI, or Visual Approach Slope Indicator, is a lighting system which provides visual descent information to a runway. 2-bar VASIs can be seen from about 3 to 5 miles during the day and up to 20 miles at night. When properly positioned on the VASI, the aircraft will have safe obstruction clearance within plus or minus 10 degrees of the extended runway center line and to 4 nautical miles from the runway threshold. When using VASI, a descent should not be started until the airplane is aligned visually with the runway. The runway or runway lights are used for proper course guidance. The most commonly installed VASI consists of 2 bars, near and far, situated alongside the runway. The basis of VASI is simply identifying the color difference between red and white. You see either red or white from either bar depending on height. If you see white, you will touch down after passing a beam of that bar. If you see red, you will touch down before passing a beam of that bar. Since the goal is to touch down between the near bar and the far bar, some pilots remember proper orientation with VASI by using the phrase, "If you see red over white, you are all right." This means you're on the proper glide path. Unless required for obstruction clearance, all visual glide slope indicators are set to provide a visual glide path that is 3 degrees to the horizontal. A pilot on the correct glide path, using a 2-bar VASI, would see the far bar as red and the near bar as white. Below the glide path, both bars would be red, and above the glide path, both bars would be white. A system with all light units installed in a single row is called a Precision Approach Path Indicator, spoken PAPI for short. If you can use a VASI, the PAPI is going to be a snap. There are 2 and 4 light systems. We'll begin with the 2-light version. Just like the VASI, what you're shooting for is a combination of red and white. If both lights are white, you are too high. If you see all red, you are too low. The 4-light PAPI system gives you varying degrees of high and low. The more white you see, the higher you are. The more red you see, the lower you are. If you see all red, you might be dead, a morbid reminder. This is something you don't want to see using a PAPI or a VASI. You may also see a tricolor visual glide slope indicator. It's a single light unit that shows the pilot a 3-color visual approach path to the runway on which the indicator is installed. If you're on the glide path, you'll see green. Below the glide path, you'll see red. Above the glide path, you'll see amber. Be aware when using this system, if you descend from green to red, you may see a dark amber color as you transition from green to red. Likewise, as you ascend from red to green, you may see the dark amber color as you transition. The useful range is about 1/2 to 1 mile during the day and up to 5 miles at night, depending on visibility conditions. During the day or night, a pilot can experience many different illusions in flight, and some can lead to landing errors. Surface features and atmospheric conditions can create illusions that mislead your ability to properly judge height above and distance from a runway threshold. Some are common to both day and night, and if you remember from Volume 3, they're caused by narrow, wide, upsloping, and downsloping runways, and atmospheric conditions such as rain, haze, or snow. At night, there are some additional illusions in flight, and some can lead to landing errors. For example, When landing over darkened areas, the illusion can be that the airplane is higher than it actually is. Also, straight lights along a road can be mistaken for runway lights. Plus, bright runway lights with few lights illuminating the surrounding area may create the illusion of less distance to the runway. Conversely, dim runway lights with few lights illuminating the surrounding area to provide height information may cause a pilot to fly a lower than normal approach. At night, inexperienced pilots often have a tendency to make approaches and landings with excessive airspeed. Every effort should be made to execute the approach and landing in the same manner as done during the day. Be aware of these illusions and anticipate them during approaches, and use visual glide slope indicators when they are available.
It's dark out there and things are different in the dark, but there's no reason that night flying should be difficult or any more hazardous than flying in the daytime. It's just different. There aren't a lot of regulatory differences at night, but there are differences in techniques and procedures. And there's one very important human factor difference, which leads me to ask, how old are you?
The reason I ask is that as your eyes age, night vision is affected first. If you go night flying and find you're having difficulty reading charts, it's probably because your old eagle eyes are used to more light.
I was a perfect 20/10 on vision until I was 40 years old, or at least I thought I was. And then one night I had to get my 9-year-old son to read charts for me on an instrument approach. Well, the next day I went scurrying to the eye doctor, and the first question he asked me was the question I asked you a while ago. How old are you? I told him I was 40, and he laughed and he said that happens to everyone when they're 40. So I got some magnifiers to use reading charts at night and went on passing my FAA physicals without glasses for another 5 or 6 years.
That little vignette sort of illustrates the major difference encountered in night flying. You can't see as well, so you have to develop techniques and procedures to work around this. For example, if you take off and climb out over an area where there are few or no lights, maintaining attitude by visual reference to a horizon will be quite difficult, if not impossible. This is actually instrument flying, so you need ability in that area to do it safely. Another example. In the daytime, you're probably getting pretty good at estimating altitude in the pattern without looking at the altimeter. That doesn't work at night, and frequent checks of the altimeter are required to verify safe altitude. On base leg in the daytime, a safe altitude is verified at a glance. There's a big difference at night. Night flying, though, can be both beautiful and rewarding.
I recall flying down the East River by Manhattan Island one crisp winter night and looking at the lights of New York City. It was just a totally beautiful sight, one that I'll recall forever.
There are several FAA flight information publications you will use during your flying career. These include the Aeronautical Information Manual, or AIM, Airport Facility Directories, and Notices to Airmen. The Aeronautical Information Manual provides basic flight information and ATC procedures for safe flight in the U.S. National Airspace System. The AIM contains the fundamentals required to fly in the United States and provides instructional and educational material. The AIM also contains items concerning medical factors, flight safety, and a glossary of terms used in the air traffic control system. The AIM is available by subscription and is updated approximately every 6 months. Another operational publication you will use is the Airport Facility Directory. This publication is issued in 7 volumes, with each volume covering a specific geographic area. The AFDs are designed as a pilot's operational manual containing all airports, seaplane bases, and heliports open to the public. Each volume is indexed alphabetically by state and city, and all pertinent information about an airport can be found in the AFD. This information includes communications data, navigational facilities, and special notices and procedures. This publication is also available through subscription and is issued every 56 days. During pre-flight planning, you will need to check the Notices to Airmen, called NOTAMs for short. These notices are considered essential to flight safety and contained information not known sufficiently in advance to publicize by other means. One type of NOTAM you will need to check is a NOTAM D. They are called D NOTAMs because they are transmitted distantly. The Aeronautical Information Manual describes D NOTAMs as containing time-critical information which may affect safety. This NOTAM is stored and is available until canceled and concerns changes relating to facilities or hazards that may exist. For example, information concerning an airport closure or navigational facilities which are not in operation may be given in a NOTAM D. NOTAM L is the second category of NOTAMs. L NOTAMs are circulated locally by voice or other means such as the telephone. This NOTAM is issued to satisfy local user requirements. Men and equipment crossing a runway or a taxiway that is closed may be classed as a NOTAM L. A NOTAM L will give information that is of a nice-to-know advisory nature. They are given to a pilot upon request before departure, while en route, or prior to landing. There are also FDC NOTAMs that are regulatory in nature. These are given system-wide dissemination and are issued to establish restrictions to flight or to amend charts. An example would be if an airport is permanently closed. NOTAMs, as well as other current information pertinent to a flight, are available from flight service stations. Before we look at the charts, a word of caution. Don't ever use out-of-date charts or publications because aeronautical data changes frequently. To be safe, check the effective dates and replace all out-of-date charts and publications. It's a good practice to throw away the old ones. Consult the aeronautical chart bulletins in the airport facility directory and NOTAMs for any changes that may have occurred during the effective dates of a chart or publication. Some charts you'll become familiar with are the Low Altitude Planning Chart, World Aeronautical Charts, Sectionals, and VFR Terminal Area and Flyway Planning Charts. The IFR-VFR Low Altitude Planning Chart is useful for routing long cross-country trips in the United States. The eastern half of the U.S. is on one side, the western half on the other. It depicts airways, nav aids, airports, special use airspace, selected population areas, prominent bodies of water, and more. The scale is 1 inch equals 47 nautical miles. Jet navigation charts produced by the Defense Mapping Agency can also be used for pre-flight planning. The jet navigation charts 43, 44, and 45 cover the 48 states and are scaled 27.43 nautical miles to the inch. Sectional and World Aeronautical charts are relatively large-scale charts. A 582 nautical mile trip from Wichita, Kansas to New Orleans requires 5 sectional charts. World Aeronautical charts are designed for navigation by moderate-speed aircraft. WAC charts are revised annually, with the exception of some Alaskan, Mexican, and Caribbean charts, which are revised every 2 years. The information shown on these charts includes airports and navigation aids, cities, principal roads, railroads, distinctive landmarks, and drainage. Hills and valleys, what is called relief, are shown by spot elevations, contours, and gradient tints. The scale used on World Aeronautical charts is 1 inch equals 13.7 nautical miles, or 16 statute miles. Airspace is also shown on WAC charts. Because of its importance, we'll be discussing airspace in a separate section later in this volume. Sectional charts are designed for visual navigation of slow and medium-speed aircraft. Each chart is named for a major city within the area of coverage. You should have little difficulty in reading these charts, since in many ways they are similar to automobile road maps. These charts use a scale of 1 inch equals 6.86 nautical miles, or 8 statute miles. We'll take a closer look at sectional charts in just a moment. VFR terminal area charts are similar to sectional charts in that they are designed for visual navigation of slow and medium-speed aircraft. As the name implies, these charts are used in congested terminal areas since they provide greater detail and clarity of information. The scale is 1 inch equals 3.43 nautical miles, or 4 statute miles. Printed on the back of the terminal area chart is the VFR Flyway Planning Chart. It identifies flight paths clear of major controlled traffic flows. Some terminal area charts feature VFR waypoints marked with a 4-point star. VFR waypoints have a non-pronounceable 5-letter name beginning with VP, and their location is pre-programmed into most GPS navigators. Most VFR waypoints are co-located with visual checkpoints, marked with a magenta flag. Visual checkpoints can be used to identify your position to ATC. However, the 5-letter VFR waypoint identifier should not be used in communications with air traffic control. The sectional, VFR terminal area, and VFR flyway planning charts are revised every 6 months. The chart type most frequently used in private pilot training is the sectional. It's also the chart type used on the FAA private pilot written tests. The sectional chart name is shown at the top. Cincinnati in this example. Effective dates are found below the chart name. The names and coverage area of all sectional charts available for the United States are shown on the map. Cincinnati is shaded to show this is a Cincinnati sectional. The magenta boxes mark locations covered by a terminal area chart. Notice the north-south arrows at the top. Opening the chart in the direction of the north arrow shows the northern half of the area covered by the sectional chart. Looking at the other arrow, you'll see that the word south is printed upside down. When the chart is opened in this direction, it's upside down as well. Upon turning the chart upright, you'll find the southern half of the area covered by the sectional chart. Before we go any further, you must understand how the world is divided for navigation purposes. An imaginary line called the equator divides the world into 2 equal parts, the northern hemisphere and the southern hemisphere. From the equator to the North Pole is an angular distance of 90 degrees. At each 1 degree increment on this arc, there are imaginary lines running parallel to the equator. They are called parallels, or lines of latitude. These parallels of latitude are used to describe navigational positions on the Earth. The regulation writers like to call the lower 48 states the contiguous, or conterminous states. To avoid confusion, we'll also use the language of the regulations. The conterminous 48 states lie between 25 degrees and 49 degrees north latitude. A position of 39 degrees north latitude would be located somewhere on a line 39 degrees north of and parallel to the equator. Lines of longitude, known as meridians, cross the equator at right 90-degree angles. Each meridian is drawn from the North Pole to the South Pole. These lines are used to determine positions east and west on the Earth. The starting point, 0 longitude, is called the prime meridian. By international agreement, this line passes through Greenwich, England. The prime meridian and the 180-degree longitude line have the Earth vertically. Longitudes on the eastern half are said to be east longitudes, and vice versa for the west. The lower 48 states lie between 67 and 125 degrees west longitude. A position of 77 degrees west longitude would be somewhere on a line 77 degrees west of the prime meridian. If we find a position of 39 degrees north latitude and 77 degrees west longitude, we'll locate Washington, D.C. From this example, you can see a specific position on the Earth's surface can be located by reference to its latitude and longitude. Traditionally, latitude is always given first, followed by longitude. On sectional charts, the degree lines of latitude and longitude are shown and are further subdivided by tick marks. Each tick mark equals 1 minute. There are 60 minutes in each degree. Let's use latitude and longitude to find Claremont County Airport on the Cincinnati sectional. Refer to the East Central Airport Facility Directory, and in the Ohio section, locate the information for the airport. It's located at 39 degrees, 4.70 minutes north latitude, and 84 degrees, 12.62 minutes west longitude. For practical purposes, you don't have to use the fractions of a minute to find the airport. Here is the 39th degree of latitude, and here is the 84th degree of longitude. The tick marks now come into use. Notice, to go north toward the 40th degree of latitude from the 39th degree of latitude, you count up. So, go north 4 minutes. Count up 4 tick marks on the 84th longitude line. Don't forget to count tick marks that are obscured by map features. To go west, move left 12 minutes, counting over 12 tick marks on the 39th degree of latitude. Where the lines intersect, you will find Claremont County Airport. Don't let the lines on which you count confuse you. As you can see, the way to measure distance between the 39th and 40th degree lines of latitude is by counting on a line of longitude. Since each minute of latitude is a nautical mile, by counting the tick marks on the longitude scale, you can measure distance. For example, you can determine the distance from Claremont County Airport to Lunken Airport by marking off the distance and measuring it against the tick marks of latitude on the longitude scale. It's 10 nautical miles. Measure it against the nautical scale on the bottom of the chart if you want to double check. The only place where 1 minute of longitude equals 1 nautical mile is at the equator. This is because lines of longitude converge as they go north or south. Even though the angular distance in degrees remains the same, the distance in miles decreases. Because of this, distance can only be measured using lines of latitude. Now that we've found Claremont County Airport, let's take a look at airport symbols. On the sectional chart legend, you'll see a number of airport symbols. These are hard-surfaced runways greater than 8,069 feet. These symbols indicate runways 1,500 to 8,069 feet in length. This anchor indicates a seaplane base, and circles alone designate airports with other than hard-surfaced runways. An R inside a circle indicates a private airport with non-public use, but having emergency or landmark value. Airports with control towers are shown in blue, along with their related information. All other airports and related information are shown in magenta. Now that you're familiar with some basic airport symbols, let's now see what we can find out about Claremont County Airport. A magenta circle indicates a hard-surfaced runway, while the open space within the circle shows the approximate runway orientation. The runway is between 1,500 to 8,069 feet in length, and the airport has no control tower. We can find the actual length of Claremont County's runway by looking at the coded data provided along with the airport name. An airport's longest runway is always shown here in hundreds of feet. Claremont County's runway is 3,700 feet. Claremont County uses a standard left-hand traffic pattern. If a right-hand traffic pattern is designated for a runway, the letters RP followed by the runway number show this. Let's take a look at an airport with multiple runways. At Cincinnati-Lunken Airport, the longest runway is 6,100 feet. The L with a star means that there are runway lights which are either pilot-controlled, part-time, or available on request. An L without a star means the runway lights are left on from sunset to sunrise. The elevation of Lunken Airport is measured at the highest point on the usable portion of the landing area. The tower frequency is 118.7. A star following the tower frequency indicates a tower which operates part-time. Hours of tower operation can be found in the sectional chart legend or in the airport facility directory. Tick marks around the basic airport symbol indicate that fuel is available and the airport is attended during normal working hours. The star at the top of the circle indicates an airport rotating beacon. This rotating beacon is in operation from sunset to sunrise and uses alternate white and green flashes. A great deal of attention is given to showing the Earth's surface elevation and obstruction data on aeronautical charts. Contour lines are lines connecting points on the Earth of equal elevation above mean sea level. On sectional charts, basic contour lines are spaced at 500-foot intervals. Intermediate contour lines may also be shown in moderately level or gently rolling areas. The pattern of these lines and their spacing will give you a visual concept of the terrain. Widely spaced contours represent gentle slopes, while closely spaced contours represent steep slopes. Color tints are used to show bands of elevation. These colors range from light green for the lower elevations to brown for the higher elevations. Generally, obstruction symbols are used to show man-made vertical features that extend more than 200 feet above the ground. Examples of features considered to be obstacles to low-level flight are antennas, smokestacks, towers, and elevated cables or pipelines crossing rivers or valleys. This symbol is used to show obstacles less than 999 feet above ground level. And this symbol is used to show obstacles 1,000 feet or more above ground level. When known, the elevation of the top of the obstacle above sea level is shown. Additionally, the height above ground level is shown in parentheses, just below the elevation. Groups of obstacles are shown using this symbol. Obstacles under construction are indicated by the letters UC next to the symbol. Strobe-lighted obstruction symbols are shown as this. Maximum elevation figures are shown on the chart in quadrangles, bounded by ticked lines of longitude and latitude, and are represented in thousands and hundreds of feet above mean sea level. The maximum elevation figures are based on information available concerning the highest known feature in each quadrangle. Now we'll draw a line from Claremont County Airport to the Fayette County Airport, over to the Richmond Airport, and then back to Claremont County. Let's take a look at some of the symbols along this route. Departing on course from Claremont County, runway 4 would take you right over a major highway and an obstruction that is below 1,000 feet AGL. Next, you'll cross over a road and the small town of Owensville with a racetrack on the left. A power line with lakes on the right and left is next. Cross the power line, road, railroad, and you'll reach the small town of Martinsville. Airborne Air Park is now off to the left. The town of Sabina is on the left with a major road that leads right to Washington Courthouse. Fayette County Airport is just northeast of the town of Washington Courthouse. Departing Fayette County Airport for Richmond Airport, we will cross a railroad, road, and then Interstate 71 is indicated by the shield shown here. Another 4-lane road, railroad, and Xenia Airport are next passed. Notice the magenta flag at the town of Xenia, denoting a visual checkpoint you can use to advise ATC on your initial contact of your position if necessary. Note the bold 17 shown here. This is the maximum elevation figure, or MEF, for the highest known feature, expressed in feet above sea level for the quadrangle bounded by these ticked lines of latitude and longitude. Back on course, cross over a 4-lane highway, 2 groups of obstructions, and another 4-lane highway, and you see Moraine Air Park. 2 restricted or private airports, shown for their emergency and landmark value, are next. They're followed by an obstruction and a city with a racetrack. Another obstruction and a road lead to Richmond Airport, which has the symbol for parachuting activity. Departing Richmond Airport for Clermont County, there is a road off to the right and roughly parallel to the course that goes over to Hamilton Fairfield Airport. About halfway to Hamilton Fairfield Airport, a lake with a dam is shown. Just south of Somerville, a lighted obstruction 1,903 feet above mean sea level and 1,003 feet above the ground is depicted. Cross Blue Ash Airport, shown with a magenta flag denoting a visual checkpoint, then cross a 4-lane highway, an obstruction, one last 4-lane highway, and here's Clermont County Airport. As you can see from this short trip, reading the symbols on the sectional chart is not difficult.
Every day, the Earth turns one revolution of 360 degrees. Since one revolution is completed every 24 hours, the Earth revolves at 15 degrees per hour. Just as distance is measured in degrees east or west, starting at the prime meridian in Greenwich, England, Greenwich is also used as the starting point in time calculations. In most nations, the practice is to establish a time zone for each 15 degrees of longitude, making a difference of 1 hour between each time zone.
The conterminous United States is geographically located approximately between the 67th degree and the 125th degree of longitude. Since each 15 degrees of longitude equals 1 hour, the lower 48 states have 4 time zones: Eastern, Central, Mountain, and Pacific. For example, when the sun is directly above the 90th degree of longitude, it is noon Central Standard Time. At the same time, it's 1 p.m. Eastern Standard Time, 11 a.m. Mountain Standard Time, and 10 a.m. Pacific Standard Time. Aviation uses a 24-hour clock to avoid mistakes which could occur from failure to specify AM or PM. You might have heard of the 24-hour clock being referred to as military time. Basically, it works like this. The PM times simply continue to count up after 12 o'clock, with 1 o'clock PM being 1300. 2 o'clock is 1400. 3 o'clock is 1500. You would refer to 3:30 p.m. as 1530, and so on, up to 12 o'clock a.m., which is 0000. 1 o'clock a.m. is 0100, 2 o'clock is 0200, and so on.
The old term, Greenwich Mean Time, has been replaced with the term Coordinated Universal Time, or UTC. You will also hear UTC referred to as Zulu time.
So if you wish to convert from local time here in the U.S. to Coordinated Universal Time, or Zulu time, you add hours as shown in this table. For an example, if you depart at 10:30 Central Standard Time for a 2-hour flight to an airport in the Mountain Standard Time Zone, what will the time be when you land? The first step to find your landing time would be to convert from Central to Coordinated Universal Time. Looking at the time conversion table, you would need to add 6 hours. This gives you UTC, or Zulu time. Factor in your 2 hours for flight time, and you'll see that your arrival time will be 1830 UTC, or Zulu. The last step would then be to convert back from UTC to local Mountain Standard Time. Remember, to convert from UTC to local time, you subtract. In this case, 7 is subtracted. This gives an arrival time of 11:30 Mountain Standard Time.
Like everything else in aviation speak, the more you do it, the easier it becomes. You can probably expect a question or two on the written portion of your test on time conversions. But if you remember what we've just discussed, they'll be easy.
Every pilot has at times gotten a little bit confused when flying, and fixation can contribute to this. We tend to see what we think is the correct checkpoint, and then we concentrate on that at the expense of everything else. On a day VFR flight, you might see a town, decide it's one of your checkpoints, and head for it, only to find that you're off course. Fixation bedevils all pilots. Even airliners have landed at the wrong airport. It usually occurred at night, when an inbound airline pilot spotted the lights of an airport, decided it was the one, and then concentrated on the arrival. Today, air traffic controllers would warn the airline pilot. Most of the wrong airport landings came before the current radar system was in place, but it is an example of why it pays to be suspicious. Your first impressions might be wrong, so keep double checking. Another thing you have to do is learn to estimate distance. It's easy to see on the chart that we're supposed to pass 6 miles south of a town, but in flight, how do you tell it is 6 miles if there's no identifiable checkpoint there? I remember having trouble with this when I was learning to fly, and the way I learned it was by flying over a town I knew was 6 miles from another town, and then looking to see what the town looked like from 6 miles away. Basic but effective. Finally, inadequate planning or improper execution of the plan can lead to confusion. But rather than think of being lost, just think in terms of being temporarily misplaced. You're probably not as far from the original plan as you think, and a logical exploration of all factors will usually get you headed in the right direction.
In the section on aeronautical charts, we looked at symbols on the Cincinnati sectional. We covered an area from Claremont County Airport to Fayette County Airport, over to Richmond, Indiana Airport, and back to Claremont County Airport. Now, let's look at the navigation planning that's done on the ground for the same trip. This planning is one of the key elements of proper pre-flight preparation. We'll use pilotage, dead reckoning, and radio navigation on our trip. The only thing pilotage involves is looking out the airplane window and flying along the course by reference to pre-selected landmarks until reaching the destination. Deduced, or dead reckoning, is calculating the effect of the wind direction and speed on the airplane, so a compass heading, ground speed, time en route, and fuel required can be estimated. To radio navigate, an instrument indication helps lead the pilot along the desired course. Using a plotter, which is a device for measuring distance and direction, determine the distance from Claremont County Airport to Fayette County Airport along the course line. Some plotters have a sectional scale on one side and a World Aeronautical Chart scale on the other, so take care to use the correct side. Simply read off the nautical miles scale that it's 47 nautical miles. From Fayette County Airport to Richmond Airport measures 66 nautical miles. From Richmond Airport to Claremont County Airport is 50 nautical miles. The total mileage for the trip is 163 nautical miles. The next step is to determine the direction to each airport for our trip. In the charts section, we showed how meridians of longitude run north and south and meet at the poles. By using these same meridians, direction from one point to another can be determined in degrees, measured clockwise from true north. A course measured this way is called a true course. To determine the true course from Claremont County Airport
to Fayette County Airport, lay the plotter on the course line drawn on the chart between the airports, with the center of the protractor on a meridian. Measure the angle this line makes with a meridian. Because the course is in an easterly direction, read the angle on the outer scale. In this case, the true course is 51 degrees. From Fayette County Airport to Richmond Airport is a westerly direction, so we use the inner scale. The true course measures 280 degrees. From Richmond Airport to Claremont County, the true course is 145 degrees. If a course line is long and crosses numerous meridians, measure the course on one of the meridians closest to the center of the course, since meridians converge toward the poles.
Now that we have distance and true course, we must consider the wind direction, since it affects our heading. Wind information received over the radio for takeoffs or landings is given as a magnetic direction. This is done to eliminate confusion between true and magnetic winds, since runway headings are also magnetic. All other wind information, spoken or printed, is given as a true direction.
While flying from point A to point B, if there is no correction in heading for wind not aligned with the course, the airplane will drift off the intended track. The difference between heading and track is known as drift angle. To offset this unwanted drift, turn the airplane slightly into the direction of the wind. The direction in which the airplane's nose is pointing will be different from the true course. This is called a true heading. The combined effect of the movement of the airplane and the movement of the air results in the desired ground track. The angle formed between the heading and the course is called the wind correction angle. But there's more.
The speed of the wind also has to be considered. Think of wind as simply an ocean of air moving over the Earth's surface in a specific direction. True airspeed, the rate at which the airplane moves through the air, is not affected by the motion of the air. But the motion of the air does affect the airplane's ground speed.
If we're flying east in a Skyhawk at 110 knots true airspeed in calm air, the ground speed is going to match the true airspeed at 110 knots. If the air begins to move from the west to the east at 15 knots, the true airspeed remains the same, but the ground speed increases by 15 knots, from 110 to 125 knots, due to the tailwind. If we turn the airplane 180 degrees and head back west, the wind becomes a headwind. The true airspeed will not change, but the 15-knot headwind reduces the ground speed by 15 knots, from 110 knots to 95 knots. If a turn to the south is made and no correction for wind is applied, the airplane at the end of 1 hour will be 110 nautical miles south from where the turn was made, and 15 nautical miles to the east because of the movement of the air.
In these examples, the true airspeed remained constant at 110 knots, but the ground speed changed. That's because ground speed is a combination of the movement of the airplane with the movement of the air. Direction and speed of the wind are therefore of prime interest to a pilot.
Next, we have to consider the magnetic compass, which is the instrument used to set direction. It's a very reliable instrument, not dependent on any power source in the airplane to operate. It's also the instrument you referred to when setting the gyro-stabilized heading indicator.
However, when planning a trip, you have to take into consideration two factors which affect magnetic compass indications. These are magnetic variation and compass deviation. By definition, variation is the angle between true north and magnetic north at any given location.
The magnetic North Pole is actually located in Canada, more than 1,000 miles from the true North Pole.
On sectional and world aeronautical charts, the amount and direction of variation, which change from time to time, are shown by means of broken magenta lines called isogonic lines. These connect points of equal variation. The line that connects points at which there is zero variation between true north and magnetic north is called the agonic line. What this means is that on the east coast, the magnetic compass needle will point to the west of true north. On the west coast, the needle will point to the east of true north. Roughly, on a line through the western Great Lakes into the Gulf of Mexico, true and magnetic north coincide. Since courses are measured on meridians pointing to true north, but flown using a magnetic compass that points to magnetic north, a method of converting from true to magnetic direction is used. This conversion is done by adding or subtracting variation as shown by the nearest isogonic line on the chart. For the next illustrations, assume there is a no wind condition. To fly a true course of 51 degrees from Claremont County to Fayette County Airport, check the nearest isogonic line. It's 5 degrees west. This amount is added to 51 degrees to obtain a magnetic course of 56 degrees. Let's look at another example. Assume that we are in the Los Angeles area, where the variation is 14 degrees east. To fly a true north course of 360 degrees in this area, you must subtract 14 degrees and fly a magnetic course of 346 degrees. A good way to remember if you add or subtract variation is by using the verse, "East is least and west is best." The rule is true when you start from true. What this means is, if the variation is east, it's least, so you subtract. If it's west, it's best, so you add. This is valid as long as the conversion is from a true course to a magnetic course.
The other factor affecting magnetic compass indications is deviation. Deviation is the deflection of the magnetic compass from its normal reading caused by some magnetic influence in the airplane itself.
Every airplane must have a compass correction card. The card is filled out by the manufacturer when the airplane is new. It's revised by an authorized person whenever work is done on the airplane that may affect the compass, such as when new radios are installed. The compass card is usually mounted close to the compass and shows any addition or subtraction necessary to correct for various headings. The corrections are usually shown at 30-degree intervals. 60 degrees is closest to our course of 51 degrees, so we'll subtract 2 degrees from our magnetic heading to get our compass heading. A compass heading is the reading that's followed to achieve the desired course. A good way to remember the steps to determine compass heading is by using the verse, "TV makes dull children." What this means is that after measuring true course and applying the wind correction, a true heading can be determined. Next, apply variation to get the magnetic heading. Finally, correct for deviation, and you arrive at a compass heading. The best way to keep a record of all these calculations is by using a flight log. There's one included on most flight plan forms.
In addition to distance in calculating the compass heading, we also want to determine the estimated time en route, ground speed, and how much fuel will be required. All these calculations can be done using either pencil and paper or a flight computer, of which there are two types. There's the old mechanical E6B, which is just a circular slide rule. Also, there's an electronic type, which is quickly replacing the old E6Bs. For our flight planning, we'll use the electronic type because of its accuracy and ease of use.
We will also need the pilot's operating handbook for our specific airplane, since it's the only source of some additional information we need for our calculations. This calculator expresses all airspeed problems with temperature in Celsius, altitude in feet, speed in knots, and distance in nautical miles. These are the units most often used in aviation. The weather briefing forecasts winds at 3,000 feet to be from 340 degrees at 9 knots. The temperature is 5 degrees Celsius on the ground at Claremont County Airport. Therefore, using the standard lapse rate of 2 degrees C per 1,000 feet, we can estimate the temperature at 3,000 feet to be about 1 degree Celsius. On the trip, we'll plan to fly no higher than 3,000 feet. We'll navigate the first leg from Claremont County Airport to Fayette County Airport using dead reckoning and pilotage, and fly at an altitude of 3,000 feet. To calculate the dead reckoning information for this leg, we need first to determine true airspeed. Use the graphs or tables in the performance section of your pilot's operating handbook to do this. Select the cruise performance that best fits your needs. On the first leg, we will use a true airspeed of 115 knots. We'll double-check all the true airspeed figures once we're in the air. The next step is to select heading and ground speed. Press Enter and put in the wind direction of 340 degrees. Now, enter the wind speed at 9 knots and the true course of 51 degrees. Enter the true airspeed of 115 knots, and the answer for ground speed is 111.7 knots with a heading of 46.8 degrees. We'll round these to 112 knots and 47 degrees. The 47-degree heading is only corrected for the wind. We still have to add 5 degrees west variation, which we get off the sectional chart, and subtract 2 degrees for deviation from the compass correction card in the airplane. Our compass heading is 50 degrees. This is the direction we'll follow on the compass as we start our flight. Now, let's figure the time required to fly the first leg. Select Leg Time, press Enter, and follow the prompts. Flight time will be 25 minutes and 14 seconds. Figure it at 25 minutes. The next 2 legs will require 60 minutes of flight time, so the total flight time for all the legs is 1 hour and 25 minutes. Since we'll be landing at each airport, let's figure an additional 5 minutes will be needed for each leg to cover climb to altitude, descent, pattern, and taxi time. This raises the total time to 1 hour, 40 minutes. Remember also, federal aviation regulations require that day VFR flights must have enough fuel to fly to the first point of intended landing, and, assuming normal cruising speed, to fly after that for at least 30 minutes. To cover this fuel requirement, add 30 minutes to the 1 hour and 40 minutes trip time to get a total time of 2 hours and 10 minutes. Now, let's figure the total fuel required for the trip. Select Fuel Required and press Enter. As prompted, enter time required at 2 hours and 10 minutes and press Enter again. Find the fuel burn rate in the pilot's operating handbook. Enter the rate of 9 gallons an hour for the Skyhawk. The amount of fuel required for the trip, plus reserve, will be 19.5 gallons. Since the Skyhawk holds 53 usable gallons, having enough fuel presents no problem. Also, a check of the airport facility directory shows fuel is available at our destination airports if more is needed for any reason. Since we will be navigating the first leg using pilotage, let's select a few checkpoints. We will use the town of Owensville and the racetrack, since they are close to the Claremont County Airport. This will help us get started in the right direction. The next checkpoint will be the town of Midland, a road, and a railroad. This will put us about 20 nautical miles from Claremont County Airport. Next up will be Airborne Air Park on the left. Now we are 28 nautical miles from Claremont County Airport and have approximately 17 nautical miles left to go. Next, we should see the town of Sabina off to the left and the town of Washington Courthouse over the nose of the airplane. The chart shows the airport is just north or above the town, with a railroad track, road, and obstruction close by. On this and all trips, take note of the airports along the route in case a diversion to one is required. We'll also take along a St. Louis sectional in case we need or want to go farther west into Indiana. We're planning on landing at Fayette County Airport. A check of the airport facility directory shows one runway, 422. It's 5,100 feet long, 75 feet wide, and is paved with asphalt. The CTAF is Unicom on 122.8, and the field is attended from 1400 to 2300, Monday through Friday. 100-octane fuel is available. On the second leg from Fayette County Airport to Richmond Airport, we'll use pilotage and dead reckoning over to around Moraine Air Park. From there, we'll tune in the Richmond VOR on frequency 110.6 and use it to radio navigate to the Richmond Airport. We'll double-check our position by getting a from reading on the Dayton VOR on frequency 114.5. We'll back up the radio navigation with pilotage and dead reckoning. We'll also check our ground speed to see if our pre-flight computations for flight time and fuel are valid or need to be updated. On the third leg, we'll radio navigate from the Richmond Airport VOR to the Hamilton area, and then tune in the non-directional radio beacon at Claremont County Airport on frequency 245 to guide us to the airport. Again, we'll back up the radio navigation with pilotage and dead reckoning. On this cross-country plan, you've seen how long trips are nothing more than a series of short trip legs strung together. Even as airliners span the globe, they do it the same way, from point to point. Granted, their equipment is more sophisticated, but the principle's the same. Later in this volume, we'll actually fly this trip.
Planning a flight carefully can help avoid surprises, and surprises are something that we really want to avoid in flying. But everything can't always go exactly according to plan. We all know that. So if we put a little bit of effort in our flight planning into looking at contingencies and alternate plans, we can save ourselves a lot of trouble later on if something goes awry. It is helpful to review those alternatives, to look at possible diversion airfields, places to land along the way should the need arise.
We might draw a line on the chart from here to there, but instead of thinking of it as a line when we study the chart, it's better to think of it as, say, a 20 or 30 mile wide swath. What might terrain or obstruction considerations be if you stray off course? We want to have an idea of obstructions, terrain, airports, and landmarks located within this swath all the way from here to there. One vital element of planning relates to fuel. The leading cause of engine failures is, you guessed it, fuel exhaustion, or running out of gas. It has happened in airline aircraft, military aircraft, and general aviation aircraft. The only way never ever to be exposed to the hazard of fuel exhaustion is to plan very conservatively.
Some say that the only time you can have too much fuel in an airplane is when it's on fire. Perhaps that's taking it a bit far, but do plan to land with at least an hour's fuel in the tanks.
The law requires less, 30 minutes by day and 45 by night, but what's legal is not always safe. Also, when calculating the amount of fuel that will be required to fly the leg, double the forecast headwind component or halve the tailwind component for the purpose of fuel planning. That way, if the forecast is incorrect, you're less likely to be surprised.
So, plan those flights so that Plan A is primary, backed up by Plan B and Plan C and Plan D and however many it takes. It is fun to vicariously fly a flight, to study the chart, to look at the airports and the landmarks along the way. Then, if when you start out on your solo cross countries, something slightly out of the ordinary happens, it'll make it a lot easier for you.
There are several types of air navigation systems in use today, each serving specialized purposes. Navigation systems include any method a pilot uses to follow a predetermined flight path over the Earth's surface.
A navigation system may be totally aircraft-based, such as an inertial navigation system, which does not require outside visual, radio, or radar contact. Or it can be entirely ground-based, with ground radar continuously monitoring the position of the aircraft and navigational guidance given to the pilot over the radio.
The most common system uses a combination of ground and airborne equipment. Ground equipment transmits signals to airborne receivers, and pilots then determine and control ground track on the basis of instrument indications. The Very High Frequency Omnidirectional Range, abbreviated VOR, and sometimes called OMNI, is the primary navigation system for civil aviation.
Military and naval aviation uses a comparable system which transmits data on ultra-high frequency called Tactical Air Navigation, or TACAN. Most VOR sites also have an operating TACAN. The combination of the stations is called a VORTAC. A VORTAC has two distinctly different transmitters and antenna systems at the same site. For now, our discussion will deal only with the VOR, and we'll refer to both VORs and VORTACs as VORs. The VOR station is easily spotted from the air. It is a small, low building topped with a flat white disc which houses an antenna system. This is the sectional chart symbol for a VOR. Here is the symbol for a VORTAC. The frequency for the VOR is shown in a box near the station symbol. Sectional charts do not show TACANs. A compass rose is centered on the VOR symbol. The compass rose and the VOR are aligned with magnetic north. Everything else on the sectional chart is oriented with true north. In sections of the country where there is considerable magnetic variation, the compass rose appears to be tilted. Pilots can select 360 different courses when navigating with reference to a VOR. Courses emanating from a VOR are called radials. Radials are defined as magnetic courses from a VOR. This is the 360-degree radial extending north from the VOR, and this is the 180-degree radial extending south from the station. To keep your semantics straight, radials are the spokes which radiate from a VOR, and bearings are the courses flown either to or from a VOR. For that matter, bearings and courses are the direction flown to or from any point on the surface. The Airport Facility Directory will show unusable radials of a VORTAC, such as the Helena VORTAC in Montana. The 035 degree through the 050 degree radials are unusable below 12,000 feet beyond 25 nautical miles, among others. VOR signal reception is line of sight and varies according to the altitude of your airplane. Obstructions, or the curvature of the Earth in the direct line between the airplane and transmitting station, will block out VHF signal reception. At 1,000 feet above the altitude of the transmitting station, normal reception extends to 40 nautical miles from the station. The reception range is proportionately less at lower altitudes. VORs are identified by a 3-letter Morse code shown on charts. If a VOR is transmitting while undergoing maintenance, the station will either transmit the Morse letters TEST
or remove the identifier altogether. This is done to inform you that the VOR signal may be inaccurate or unreliable, and the station should not be used. Listening to the signal to identify the station is extremely important. First, be sure the correct station is tuned in. And second, be certain the station is operating normally. The accuracy of the VOR system depends on proper adjustment of both the transmitter and the receiving equipment. With the transmitter and receiver operating normally, accuracy is generally plus or minus 1 degree. The VOR receiver has a volume control, ident switch, and frequency selector. Frequencies for VORs range from 108 to 117.95 MHz. Pulling the ident switch allows you to hear the Morse code identification along with any voice transmissions over the VOR. With the switch pushed in, the Morse tones are suppressed, making it easier to hear voice transmissions. The VOR indicator has an omni-bearing selector, abbreviated OBS, a course deviation indicator, a CDI for short, and a to/from indicator. There are a couple of ways to show that no signal is being received or that the signal is too weak. Some indicators show an off flag. Others just do not show a to or from indication. As the name implies, the omni-bearing selector is used to select the bearing, or course. When a course is selected, the course deviation indicator shows the position of the selected course. The indications of the CDI and the to/from indicator are not affected by the heading of the airplane. At any location, if the CDI indicates the selected course is to the left, the CDI will always be to the left, no matter which way the airplane is pointed. Because you will see the same indication on all headings, the left and right information is only valid when the airplane is pointed in the same direction as the selected course. The left and right CDI indications will be correct if the airplane heading generally agrees with the course selected on the OBS. Think of the airplane as the center dot and the needle as the selected course. If the needle is centered, the airplane is on the selected course. If the CDI is pointed to the right, the selected course is to the right of the airplane. A needle to the left means the course is to the left. A full-scale deflection of the CDI represents 10 degrees. Because this information is angular, the actual distance off course depends on the distance from the station. A half-scale, or 5-degree deviation 10 miles from the station puts you about a mile off course. 30 miles from the station, the same deviation puts you about 3 miles off course. The to/from indicator shows whether the selected course will take the airplane to or from the station. Some manuals call the to/from indicator the ambiguity meter, so named because it resolves the ambiguity of whether the selected course will take the airplane to or from the station. From the north, on the 360-degree radial, a bearing of 180 degrees to will take the airplane on a course to the station. The same course from the south will take the airplane from the station. The to/from indicator measures the radials that are at right angles to the course set on the OBS. When crossing those radials, the to/from indicator will flip even if the airplane is miles away from the station. Remember, VOR indications are not changed by the heading of the airplane. In all 3 airplanes, with the OBS set to 180 degrees, the CDI is centered with a from indication. Turn the OBS to 360 degrees, and the CDI will again be centered with a to indication. The heading of the airplane only affects how long the CDI will remain centered. If the airplanes continue on these headings, the CDI will not stay centered.
Orientation is a word you'll hear a lot. The dictionary defines it as determining one's position. If you have to determine your position, you probably aren't lost, but merely not sure of your exact position.
As an example, flying from the Clark Airport to the Mineral Wells Airport using the VOR to locate yourself is fairly easy if you follow some simple steps. First, tune the VOR receiver to a nearby VOR. Remember, you aren't really lost. You know that you are in a certain area. After you have identified the station, turn the OBS to center the CDI. Don't rush this. Spinning the OBS too fast will make the CDI move like a windshield wiper. When the CDI is centered, you have all the information you need. Read the course from the OBS and to or from on the to from indicator. If the OBS is on 194 degrees with a from indication, you can draw a line from the MILSAP VOR on the 194 degree radial and know that you are located somewhere on that line. To fix your position on this line, you could look for a landmark or find your position in relation to another VOR. The Glen Rose VOR is close to your line of position. Tune to the Glen Rose VOR. Repeat the process, and the CDI centers on the 310-degree radial from the Glen Rose VOR. Your position is where the 310-degree radial from Glen Rose intersects the 194-degree radial from MILSAP. To find a bearing to the MILSAP VOR, tune in the VOR. Set the OBS to center the CDI with a to indication. The OBS is on 014 degrees, so turn the airplane to a heading of 014 degrees. As you fly inbound, make heading changes to keep the CDI centered. As you get closer to the station, the heading corrections needed will be smaller. This is because radials are like the spokes of a wheel. They converge at the station. Within a few miles of the station, you will notice the CDI and the to from indicator flickering. The size of this cone of confusion is relatively small at low altitudes and increases with altitude. Do not mistake this cone of confusion for station passage. Station passage is indicated when the to from indicator makes the first complete reversal to a from indication. The Mineral Wells Airport is on the 307-degree radial and 4.6 nautical miles from the MILSAP VOR. After crossing the VOR, change the OBS to 307 degrees and turn the airplane to 307 degrees. Then, make small corrections as needed to keep the CDI centered. Use small corrections because the airplane is very close to the VOR. 4 nautical miles from the station, a half-scale deflection of the CDI amounts to less than a half mile off course. You might encounter some minor course roughness on VORs. Some receivers are more susceptible to this than others. Course roughness can be caused by rough terrain and appears as CDI or to from indicator fluctuations.
Like the VOR, TACAN provides line-of-sight information transmitted on ultra-high frequencies. Receiving equipment for the TACAN course, also called the azimuth feature, is generally not available for civilian aircraft. TACAN has another feature, which is a distance measuring capability. Equipment to use this feature is available and installed in many civilian aircraft.
Distance Measuring Equipment, DME, does away with the need for a crossfix from another VOR to establish the aircraft's position. The pilot selects the frequency of the VORTAC on the DME. The airborne DME sends a signal which triggers a response from the ground station. The airborne equipment measures the time the round-trip signal took and presents the information as nautical miles. Some DMEs also show ground speed and time to the station. Some VORs only have the DME feature of the TACAN. These are called VOR DMEs and are shown on charts by the VOR hexagon symbol inside a square. Although VOR DMEs aren't equipped for TACAN use by the military, civilian pilots can get distance from the station if their airplane is equipped with distance measuring equipment.
A VOR receiver used under instrument flight rules must have been operationally checked for accuracy within the past 30 days. While this check is not required for VFR, it is certainly a good operating practice. There are several ways to check the accuracy of a VOR receiver.
The Airport Facility Directory lists designated ground and airborne receiver checkpoints. At these locations, a specified radial should be received. Allowable error for VFR is not prescribed. For IFR, the ground check error cannot exceed 4 degrees. Maximum error using the designated airborne check is 6 degrees. Another way to check the VOR is the Very High Frequency Omni Test, or VOT. VOTs provide a convenient means of determining the accuracy of a VOR receiver while the airplane is on the airport where a VOT is located. Use of VOTs while airborne is strictly limited to those areas and altitudes specified in the Airport Facility Directory. VOTs are identified by either a continuous tone or a series of dots. VOTs transmit the 360-degree radial in all directions. No matter where the aircraft is located, the VOR receiver will indicate the 360-degree radial. Electronically, the aircraft is always located north of the VOT. There is no prescribed accuracy requirement for VFR use. For IFR, the CDI must center within 4 degrees of 360 degrees from, or 180 degrees to.
It's recommended that VOR receivers be recalibrated annually. Radio repair shops have a test signal generator, similar to the VOT, which is used to calibrate VOR receivers. As Dick Collins said earlier, don't think of yourself as lost, just temporarily misplaced. With the help of nearby VORs, you can easily pinpoint your position.
Most of the references to navigation in private pilot training are to VORs and NDBs and compasses and clocks and charts. The charts will be around, but there's a new form of navigation coming that will replace the VOR and the NDB in the not-too-distant future. GPS stands for Global Positioning System. It uses a constellation of 24 satellites to provide very accurate navigation anywhere in the world. While there's currently no emphasis on GPS in the FAA tests, there may well be a GPS navigator in the training airplane that you fly, or you may have bought yourself one of those great portable GPS navigators available through Sporty's catalog. We're not going to teach you how to use GPS here, but we think it important that you know some of the advantages of GPS. GPS units have a database, and most of these include every radio navigational point that is charted by the FAA, plus all the public use airports. Every VOR, NDB, and intersection is there. With GPS, you can get information on navigating direct to any point in the database, or you can put in a flight plan that will guide you from one point to another, and on to your destination. GPS gives information on your position in relation to a desired course, like a VOR, and gives distance and ground speed, like a DME, and GPS is more accurate than either. GPS units, whether portable or installed in the panel, offer a lot of other information too. They may have all the frequencies for an airport, airport diagrams, maps of the terrain, and regulated airspace, plus the time of sunset and sunrise, for airports, and many have a vertical navigation feature that helps in descent planning and management. GPS will tell you the track being made good over the ground. Track is an especially important GPS feature because when flying cross-country, track is what gets you where you're going. GPS takes all guesswork out of correcting for wind drift. If you keep the track matched to the bearing to the next point, you'll go there. Newer GPS units update track so quickly that in shallow bank turns, the track information is as good as that you get from the heading indicator, and it's much better in turns than information from the magnetic compass. Most GPS navigators will tell you how long you've been flying and give you an ETA for the destination. If you want to know about the nearest airports, that information is but a button press or two away. Despite the training emphasis on VORs and NDBs, there are a lot of pilots around, and I'm one of them, who've used GPS as a primary form of navigation for years. GPS is wonderful. It's more precise, it makes navigating easier, and it puts a world of information at your fingertips. LORAN, incidentally, is a different system based on ground stations, and while it has little formal role in the system, it does what GPS does. It'll be around for a while, and you may fly an airplane with a LORAN navigator installed. There are different brands of GPS navigators, and there's really no standardization on how to operate them. That's good because it leaves each manufacturer to try to do better than the others and to pack more features into their navigators. Good old competition, in other words. Most GPS navigators can be learned in a relatively short period of time using the instructions manuals. Sporty's has tapes on using GPS for en route navigation as well as on flying GPS instrument approaches. GPS is there to use now, and while it may not be emphasized in private pilot training, once you get your private certificate and start exploring the sky on your own, you'll find GPS a wonderful way to meet the challenge of navigation.
Many general aviation airplanes are equipped with automatic direction finding radio receiving equipment. To navigate using the ADF, the pilot tunes the receiving equipment to a ground station known as a non-directional radio beacon, or NDB. These low and medium frequency non-directional beacons were among the earliest electronic navigation aids. The word non-directional refers to the fact that the signal radiates from the antenna equally in all directions.
Non-directional beacon symbols are printed in magenta on sectional charts. The frequency for the beacon is indicated in a magenta box near the beacon symbol. Non-directional beacons are sometimes called homers because they are used to home to the station. NDBs normally transmit in the low-medium frequency band on frequencies from 190 to 535 kilohertz. The ADF, which stands for Automatic Direction Finder, receives non-directional beacons as well as AM broadcast stations. Commercial broadcast stations are usually more powerful and can be received at greater distances, but they have the disadvantage of infrequent identification. The ADF receiver has a frequency selector and may have a function switch with receiving and ADF positions. In the ADF position, the needle on the ADF indicator will point to the selected station. The ADF indicator could have a fixed card with the 0 position always at the 12 o'clock position, or have a card which can be rotated to put the airplane heading at the 12 o'clock position. Think of the airplane as being in the center of the ADF indicator, flying toward the top of the indicator. If the needle points up, the station is in front of the airplane. If the needle points down, the station is behind the airplane. If the needle is pointing to the right, the station is to the right. If the station is to the left of the airplane, the needle points to the left. One way to find the course to the station using a fixed card indicator is to turn the airplane until the needle is pointing to 0. The airplane is now pointed directly toward the station, and the heading indicator shows the course to fly to the station. To find the course to the station without turning the airplane, imagine where the ADF needle would point if it were moved to the heading indicator. Mentally pick the needle off the ADF indicator and without letting it change angle, place it on the heading indicator. When moved to the heading indicator, the imaginary needle points to the course to the station. Both the fixed card and rotatable indicators are usually marked starting at 0, increasing clockwise the 360 degrees of the circle. The number the ADF needle points to is called the relative bearing. The relative bearing is the angle between the longitudinal axis of the airplane and the course to the station, measured clockwise. Put another way, the relative bearing is the degrees of right turn needed to point the airplane towards the station. A relative bearing of 120 degrees places the station to the right and behind the airplane. To find the course to the station, add 120 degrees to the heading of the airplane. This gives the same result as turning the airplane 120 degrees to the right. A relative bearing of 230 degrees places the station behind and to the left of the airplane. Turning right 230 degrees would probably not bring a smile to your instructor's face. At the completion of the 230-degree turn, the airplane would be pointing to the station, but it would be the long way around. Making a 130-degree turn to the left would also point the airplane to the station and probably bring a smile and compliments.
The Aeronautical Information Manual defines bearing as the horizontal direction to or from any point, usually measured clockwise. Bearings must always be described as being either to or from. Reciprocals are opposites, which means they will be 180 degrees apart.
For instance, the reciprocal of 50 degrees to the station is 230 degrees from the station. In the airplane, reciprocals are easy. Just use the heading or ADF indicator. Reciprocals are across the dial from each other. The reciprocal of 220 degrees is 40 degrees. The reciprocal of 130 degrees is 310 degrees. The arrowhead of the ADF needle shows the relative bearing to the station, so the tail of the needle indicates the relative bearing from the station. Transposing the ADF needle to the heading indicator has the arrowhead pointing to the magnetic course to the station. The course from the station is the reciprocal of the course to the station. Doing it the easy way, it is the number at the tail of the ADF needle that has been mentally placed on the heading indicator. Course to the station is 160 degrees. Course from the station is 340 degrees. Here, the course from the station is 60 degrees. The course to the station is 240 degrees. Remember, relative bearing is always in relation to the longitudinal axis of the airplane and is measured clockwise. A relative bearing of 0 always means the station is in front of the airplane. A 90-degree relative bearing always places the station off the right wingtip. The station is directly behind the airplane when the relative bearing is 180 degrees. A 270-degree bearing always puts the station off the left wingtip. If the ADF indicator has a rotatable card, simply turn the card to place the airplane heading under the index at the top. Course to the station is shown at the arrowhead, and course from the station is found at the tail of the needle. This makes it easier to determine courses to and from the station, but it is possible to make mistakes if you forget to reset the ADF card after the airplane heading has changed. The easiest way to fly to the station using any ADF is called homing. To home to the station, simply keep the relative bearing on 0. If there is a crosswind, the ground path will be curving, but the airplane will fly to the station. The more efficient method is to track using a wind correction angle, which produces a straight ground track. Pilots are usually not trained in tracking with the ADF until they go for their instrument rating. Low-medium frequency navigation equipment has the advantage over VOR navigation in that it is not limited to line of sight. Unlike VORs, NDB signals may be usable from stations located beyond the horizon. A disadvantage of ADFs is that the receiver is subject to static in the vicinity of thunderstorms and precipitation, just like AM radio. Precipitation static caused by the static electricity generated when the airplane flies through rain or snow may make reception difficult or impossible. At night, non-directional beacons are also vulnerable to interference from distant stations.
Let's take a closer look at line crews. As you make longer and longer cross-country trips, you will need fuel away from your home airport. Most airports have at least one fixed base operator that can sell you fuel. Just as in your car on the road, you can look for the fuel company signs on the ramp. As you pull up to the FBO, as they are called, you might be greeted by a line person waving his arms. He's not simply trying to get your attention, he's directing you to your parking spot. The motions are standardized and have specific meanings, and you can study up on them in the Aeronautical Information Manual. The most common ones you'll see are a turn, come straight ahead, and stop. Only after you shut the engine down will the line person approach your airplane to take your fuel order. Some pilots choose to hang around while fueling is taking place, just to double check that the right amount and type of fuel is being put in. If your tanks are mistakenly filled with jet fuel instead of avgas, the engine will have a nasty tendency to quit running at an embarrassing moment, such as after you're airborne. Like any new experience, flying into strange FBOs will seem awkward at first, but you'll soon learn that everyone else there is probably a flying buff too. You'll see what we mean when we say that the people in aviation are indeed a community.
In the last video volume, we did not specifically discuss the weather associated with air masses and fronts. Now we take a look inside these air masses and see what happens to the weather when two air masses meet. This knowledge is important because pilots can then better judge the weather as it affects the safety and economy of a flight. Air masses are defined as large bodies of air within which temperature and humidity are fairly uniform horizontally. Air masses are created whenever a large body of air approaches and remains at a source region. Source regions, on the other hand, are characterized by fairly uniform surface conditions. An air mass is created whenever air remains at the source region long enough to acquire the temperature and moisture characteristics of the surface. Most of the modification of temperature and moisture takes place from the surface upward. So when conflicting air masses meet, the differences of temperature and moisture are greatest here at the ground and at lower altitudes. The weather which results from this conflict is also most intense at lower altitudes and tends to diminish higher up. The best source regions are large snow and ice covered polar regions, cold northern oceans, tropical oceans, and large desert areas. The middle latitudes from 30 to 60 degrees north are poor source regions. This is because the moving storm systems which dominate these latitudes do not allow air masses to stagnate. We meteorologists classify air masses according to the surface of the source region itself, and whether the air mass is colder or warmer than the surface over which it is moving. Air masses are identified using three letters. The first lowercase letter identifies the surface of the source region. C for continental, M for maritime, or a water surface. Source region is indicated by an uppercase letter, P for polar, A for Arctic, T for tropical, and E for equatorial. The last letter is lowercase, W for an air mass warmer, and K for an air mass colder than the surface over which it is moving. Air mass classification is usually not indicated on aviation weather data. Surface and source region mostly concern the meteorologist. For pilots, knowledge of the temperature of the air mass relative to the underlying surface indicates relative stability and is useful. A W air mass is cooled from below, which implies stable conditions, with smooth flying, stratus clouds, fog, and poor visibility. Precipitation, if any, would be widespread drizzle and rain. Applying the same reasoning, the K air mass would indicate heating air from below and therefore unstable conditions, With unstable conditions, pilots can expect rough air to 10,000 feet or so, cumuliform clouds, and if there is precipitation, it is large drop and localized or showery. As air masses move from their source regions, they come in contact with air masses of differing properties. The zone between contrasting air masses is called a front. The concept of fronts was developed by Scandinavian meteorologists during the First World War. What was happening between air masses reminded them of a battle between armies. Across this battle zone, temperature, humidity, wind, and air pressure can all change very quickly over a very short distance. There are some things that all fronts have in common. For instance, all fronts are in troughs which extend from lows. Air masses, on the other hand, are highs, meaning the air pressure within the air mass is higher than the surrounding atmospheric pressure. The lowest pressure in each air mass is found at the boundary between them. This boundary is called the front. The cold air is on the bottom and the warm air is aloft in all fronts, and a front always slopes over the cold air. In a very strong front, the slope may reach to the top of the troposphere, called the tropopause. From a pilot's viewpoint, the position of a front aloft is just as important as the surface position. This slope can be as steep as 1 to 50 and as shallow as 1 to 300. This means an airplane 1 mile above the surface could cross the frontal zone in as little as 50 miles from the surface position if the frontal slope is steep, or may have to fly as many as 300 miles beyond the surface position of the front if the slope is shallow. Remember, the position of all fronts aloft is always on the cold side of the surface position. A front is really a zone of change, not a line like it appears to be on a weather map. When moving across a front from one air mass to the other, the change of temperature, wind, and humidity may be quite abrupt, indicating a narrow frontal zone. But a gradual change of these properties indicates a broad, diffuse frontal zone. Temperature change is one of the most easily recognized differences you'll notice as you cross a front. Temperature change is more significant at low altitudes, but differences in cloud cover across a front may obscure temperature changes. Dew point change across a front and the change of temperature dew point spread helps identify the front and gives a clue to the differences of cloudiness and fog. And speaking of fronts, winds always change direction when you cross a front. That requires a change in heading to maintain your course. Air should flow directly from high to low pressure down the pressure gradient. But airflow is modified by the Coriolis effect, which is caused by the Earth's rotation. The wind is deflected to the right in the northern hemisphere. The final result of this modification by Coriolis is that winds aloft blow parallel to the isobars, which are lines that connect points of equal barometric pressure. Around lows, flow is counterclockwise, or what we call cyclonic. Therefore, the terms low and cyclone are used interchangeably. Flow around a high is clockwise, or what we call anticyclonic. For that reason, highs are also called anticyclones. Because surface friction reduces wind speed, and because Coriolis is proportional to wind speed, Coriolis force near the ground is less than higher up. As a result, surface winds are slower and blow toward lower pressure. The angle at which surface winds cross isobars depends on surface roughness and may be as little as 10 degrees over water and as much as 45 degrees over mountainous terrain. When crossing the front, which lies in a trough, the change in wind direction calls for a heading change to the right in order to maintain course. A heading change to the right is needed when crossing any front in any direction. Wind speed, too, may also change with the front. Pressure patterns may vary widely across fronts. The front is in the trough and the lowest pressure is at the front itself. Generally, pressure in the cold air mass will be somewhat higher than the warm air mass. In any case, there is a difference in the rate of pressure change, which makes it very important to keep altimeter settings current. Flying weather in fronts can vary from virtually clear to hazardous, including turbulence, hail, structural icing, and low ceilings and visibilities. The kind of weather you'll encounter in a front depends on the moisture available, stability of the air that is being lifted, speed of movement, frontal slope, and upper wind flow. Fronts can be classified as cold, warm, stationary, and occluded. Continuing the analogy to warfare, the front is named for the advancing air mass. When cold air advances and replaces warmer air, the leading edge of the cold air is called a cold front. The chart symbol for the cold front is a line with triangles pointing in the direction of movement. Behind me, the movement is to the southeast, and the cold air is advancing in that direction. Cold fronts typically move towards the southeast at speeds of 25 to 30 knots. Speed of movement largely depends on wind speeds behind the front. Fast-moving cold fronts have been observed moving faster than 50 knots. Cold fronts have an average slope of 1 mile vertically for every 80 miles horizontally.
Slow-moving cold fronts have a more shallow slope, so the warm, humid air can move easily up and over the front. Therefore, thunderstorms develop behind the surface position of the shallow cold front. Fast-moving cold fronts are steeper and more intense. These fronts frequently produce thunderstorms at the surface position of the front and lines of thunderstorms called squall lines 100 miles or so ahead of the front.
If warm air is advancing, replacing colder air, the leading edge of the warm air is called a warm front. Warm fronts are charted as half circles on a line pointing in the direction of movement. Here behind me, the warm air is moving towards the northeast. When compared to the cold front, warm fronts have a more shallow slope and under equal wind flow move about half as fast as cold fronts. A point to remember: frontal slope is an indicator of how wide an area will be affected by frontal weather. Because warm fronts have a shallower slope, warm frontal weather is usually found over a much wider band than cold front weather.
Warm fronts are usually, but not always, less violent than cold fronts and bring extensive areas of low stratus ceilings and poor visibilities. If the warm air is unstable, there may be thunderstorms embedded in the massive layers of stratus clouds. Because of the shallow slope and slower movement, warm fronts affect aviation for longer periods of time.
When the opposing forces on either side of a front reach a stalemate and the front moves at less than 5 knots, it is called a stationary, or more correctly, a quasi-stationary front. Here the cold and warm front symbols are alternated, like behind me, you see that. The triangles of the cold front point away from the cold air, and the half circles of the warm front point away from the warm air. The symbols pointing in opposite directions graphically indicate lack of movement. In most cases, stationary fronts resemble stable warm fronts. But if the warm air is unstable, like the air moving northeastward here, convective and thunderstorm activity could develop.
Low ceilings, visibilities, and the weather associated with the stationary front may affect an area for several days or even weeks. During the day, solar energy warms the warm side more. Along the front, the warm air mixes into the cold air, warming it, and the warm front moves northward. At night, radiational cooling is greater in the nearly cloud-free skies in the warm air, so the stationary front slowly pushes south again. These oscillations can cause any location to have alternate warm and cold air mass weather several times over a few days.
Along a stationary or slow-moving cold front, in this case a stationary front, strong lows may develop. The strong low pulls the cold and warm air together, and since the cold air travels faster than the warm air, it eventually catches up, forming what's called an occluded front. An occluded front is symbolized by warm and cold front symbols on the same side of the line, indicating direction of movement, in this case to the northeast. It's long-lived and can cause violent weather.
Winds flowing in opposite directions and parallel to the front are deflected by the bend and develop a counterclockwise or cyclonic flow. The eastern section of the front moves as a warm front, while the western section moves as a cold front. Pressure at the peak of the wave lowers and the low forms. Cyclonic circulation becomes stronger, making surface winds strong enough to move the fronts. The warm front moving northward is followed by a cold front, which moves faster, catching up with the warm front. The development and life of a cyclonic storm is closely associated with the jet stream, which means there could be severe turbulence aloft above a developing cyclonic storm. Weather associated with the occluded front is a combination of warm and cold front weather. Occluded fronts involve 3 distinct air masses and are classified as either warm or cold occlusions. The classification is based on the relative temperature of the air masses. A cold occlusion occurs when the arriving air is coldest and forces the existing warm front off the ground. That is, the arriving cold air occludes or obstructs the warm front from touching the ground. The new air is colder than the previous air, and the temperature may fall when the occluded front passes. Most occlusions in the United States are the cold occlusion type. If the new air mass is not as cold as the existing air mass, the warm front remains on the ground, and the new air is lifted. When the warm occlusion passes, the temperature may rise because the arriving air is warmer than the previous air. As these weather systems travel even further from the source region, the air is modified by the surface over which it is moving. Eventually, temperature differences equalize, causing pressure differences to do the same, and the system, fronts and all, dissipates. Not all lows are accompanied by fronts. Some lows develop wholly within an air mass and do not separate contrasting air masses. One example of a non-frontal low forms just downwind of mountain ranges. The low of the lee slopes of the Rocky Mountains can be quite a weather maker. Upslope winds across the plains can lead to low ceilings and visibilities, drizzle, fog, and snow and ice. A rapidly developing lee slopes low can make weather changes across the Great Plains very rapid. While not associated with a front, the lee slopes low can cause fronts to form by drawing together the contrasting air masses of the northern plains and the Gulf Coast, resulting in frontal weather development. A rule of thumb: be wary of the lee slopes low. Rapidly changing weather can cause a pleasant, clear sky flight to turn into a desperate search for the nearest airport, especially in winter. Thermal lows like the one found all summer over the desert southwest are a second example of non-frontal lows. Unlike the lee slopes low, a thermal low is weak, shallow, and not much of a weather maker. It may lead to a bumpy flight at low altitudes, but it does not lead to cloud and precipitation formation. Squall lines are lines of thunderstorms that form along lines of instability. While not directly associated with fronts, squall lines tend to form 50 to 100 miles ahead of and parallel to a cold front. Squall lines are indicated on a weather map by a line drawn with two dots alternating with a long dash. Squall lines frequently form in the western Great Plains along what is called the Dew Point Front, dry line, or in West Texas, the Marfa Front. A dry line is indicated by a large drop in dew point and a slight wind shift as the dry line is crossed. At night and during early morning, fog and low clouds on the east or the moist side indicate the position of the dry line. On the dry side, skies are clear. Nighttime sees the dry line moving toward the west. During daylight hours, the dry line moves to the east, and by afternoon, thunderstorms and tornadoes are frequently spawned along the boundary between the dry and moist air. Frontal weather can be tricky and can change very rapidly. A cold front which only has cloudiness in the morning may have a strong squall line forecast for the afternoon. The warm front which causes partly cloudy skies in the afternoon may bring fog, drizzle, and low clouds by nightfall.
Beware of the high-pressure good weather, low-pressure bad weather rule of thumb. While it's frequently true that high-pressure days like today have good flying weather, this rule of thumb will often fail in a spectacular display of poor weather under a high.
A good pre-flight weather briefing and a mental picture of what is happening and what is forecast to happen is essential. Checking the weather while in flight to keep the mental picture updated will provide the data necessary if a diversion has to be made.
Now let's talk more about some of the weather information to which you have access in making your flying decisions.
In the last volume, we looked at the weather depiction and radar summary charts, which are broad overview reports of the weather. We also looked at terminal aerodrome forecasts, TAFs, and hourly reports of surface observations, which are commonly called METARs. TAFs and METARs are definitive to an airport. In this volume, we'll deal with several broad-term forecasts as well as reports of actual weather conditions from other pilots. In a few moments, we'll look at the forecast charts, TAFs, and METARs we showed you in Volume 3. You'll see that forecasts can often make reliable predictions. Remember, if you check and compare radar summary charts, weather depiction charts, and hourly METARs with forecasts, you'll know how credible the current forecasts are.
Let's take a closer look at some of the sources for obtaining weather information. DUAT stands for Direct User Access Terminal. It is a government-supplied weather service available by modem and computer. Through subcontractors, the FAA makes available the weather data used by flight service personnel to give you weather briefings. You may also file flight plans through the DUAT system. Setup is self-prompting, and you may select from several options on the kind of weather data you want for your proposed flight. Basic DUAT service is free for pilots, with the FAA picking up the tab. However, the DUAT providers offer additional graphics and services for a fee. Besides DUAT, there are other weather services available from private vendors by subscription. We'll take a quick look at some you may find on your cross-country flights. DTN offers color motion radar maps, satellite pictures, forecast graphics, NOTAMs, current conditions, and textual weather, available through key-accessed menus. There are different levels of service available depending on the kind of flying you do. Weathermation is another database system of weather information presented in both graphical and alphanumeric formats. Dedicated keys allow for direct access to radar, fronts, winds, satellite pictures, and more. Plus, you can do flight planning and file flight plans using the Weathermation system. WSI also offers a variety of weather maps, radar, and textual information accessed through a simple point-and-click interface. All three systems are designed for ease of use without any prior computer knowledge. When it comes to weather, a picture is indeed worth 1,000 words.
Low-level significant weather prognosis charts are general visual weather forecasts designed for flight planning up to 24,000 feet. Prog charts provide a visual depiction of predicted weather. They are issued 4 times daily based on data at midnight, 0600, 1200, and 1800 Zulu times. There are 4 panels on the chart. The top panels forecast the weather conditions between the surface and 400 millibars of pressure, which is approximately 24,000 feet. Weather conditions at the surface are forecast by the bottom charts. The left-hand panels are 12-hour progs, and the right-hand panels are 24-hour progs. Each panel has the valid time for the forecast indicated by the letters VT in the date block. The valid time is the specific time the forecaster expects the weather conditions indicated on the panel. 12 and 24-hour indicates the time of the weather reports on which the forecast was based. Both the 12 and 24-hour charts are based on the known weather conditions which existed at 12 Zulu, May 19th. From a practical standpoint, the 12 and 24-hour label is an indication of the reliability of the forecast. Long-term forecasts are usually less reliable than those made for a shorter period. In general, the 24-hour panels tend to be less reliable than the 12-hour panels.
Weather is dynamic, it just never stands still. To determine expected conditions beyond the valid time of the 12-hour prog, it is necessary to interpolate between it and the 24-hour prog.
The surface prog outlines areas of forecast precipitation and thunderstorms. Forecast of the type of precipitation and amount of coverage is also shown. Forecast areas of IFR and marginal VFR weather are indicated on the top 2 panels. The bases and tops of forecast moderate or greater turbulence, as well as forecast freezing levels, are also shown.
The common standard weather symbols used on the prog are intermittent rain, drizzle, and snow. If we double the symbols, we indicate continuous rain, drizzle, or snow. Rain and snow symbols above a triangle denotes a shower. Showers represent precipitation that starts and stops and vary in intensity. Symbols for moderate and severe turbulence, as well as thunderstorms, like these, are graphically suggestive. Less commonly used symbols are freezing rain and drizzle, tropical storms, and hurricanes.
Symbols used for areas of predicted IFR weather, marginal VFR, moderate or greater turbulence, and freezing levels are shown between the 12 and 24-hour panels. Criteria for IFR and marginal VFR are listed inside the symbols. This is the 12-hour significant weather prog chart, valid for 00 Zulu on May 20th. There is an area of IFR weather surrounded by an area of marginal VFR weather forecast for the Northeast, extending down the coast to North Carolina. Marginal VFR conditions are also called for along the California coast. An area of moderate turbulence is predicted in the southwestern United States, extending from 20,000 feet down to the surface. Freezing levels, depicted by the short dashed lines, are forecast at 4,000 feet MSL in the north, 8,000 feet from Quebec to the Pacific Northwest, and 12,000 feet along a line from Florida out to San Francisco, plus northeast Maine, and 16,000 feet MSL in southern Texas. A freezing level at the surface would be depicted by a zigzag line. On the surface prog, a cold front is forecast to stretch from southeastern Canada to the Gulf of Mexico. Another cold front will curve south from the Dakotas to northern Utah, and a stationary front is predicted to start in Saskatchewan and extend to the northern Wisconsin area. Each front is classified by a 3-digit number that gives the type, intensity, and character of that front. The bracket points toward the front to which the number refers. Precipitation areas are bounded by dark lines. The shading implies that half or more of the area is forecast to have precipitation. If the area is not shaded, the forecast is for less than half of the area to have precipitation. 6 surface lows are forecast with troughs extending from most. Highs are predicted in the Pacific Northwest, southern Colorado, Lake Superior, and southern Indiana. The central pressure of each high and low is indicated in millibars by the 4-digit number. From prognostic charts, let's move on to area forecasts. Area forecasts are predictions of general weather conditions for an area the size of several states. 6 area forecasts cover the contiguous 48 states. Each forecast is further broken down into states, parts of states, and other geographical designations. Issued 3 times daily, each area forecast covers a 12-hour period with an additional 6-hour outlook. Area forecasts consist of 4 sections: a product header telling you where and when the forecast applies, a precautionary statement advising how to use the forecast and where to seek additional information, a synopsis, which is a brief summary of weather systems and phenomena affecting the area for the 18-hour period, and finally, a VFR clouds and weather section, which composes the bulk of the area forecast. This section gives a general description of clouds and weather which cover an area greater than 3,000 square miles and is significant to VFR flight operations. Concluding each area's clouds and weather section is the outlook for the last 6 hours of the 18-hour period covered by the area forecast. The outlook will give a broad description of flight conditions, VFR, marginal VFR, or IFR. The criteria for VFR, marginal VFR, and IFR are the same as those used and printed on the weather depiction chart. The outlook may also include significant weather phenomena such as wind, ceilings, thunderstorms, etc. As with any forecast, the area forecast is usually more accurate for the beginning of the forecast period. Checking the present weather conditions against the forecast weather is the best way to assess the reliability of the forecast. Let's go through part of this area forecast issued from Boston. The C following the 3-letter identifier indicates a forecast containing clouds and weather. This was issued on the 7th of the month at 1845 Zulu. The synopsis is valid until the 8th at 1300 Zulu. Clouds and weather are only valid until the 8th of the month at 0700 Zulu. And the outlook valid time begins at 0700 Zulu and goes until 1300 Zulu. The area covered by the forecast includes Maine, New Hampshire, Vermont, Massachusetts, Rhode Island, Connecticut, New York, Lake Ontario, New Jersey, Pennsylvania, Ohio, Lake Erie, West Virginia, Maryland, the District of Columbia, Delaware, Virginia, and coastal waters. The highlights of this forecast are found in the precautionary statements. The first is to alert you to check AirMet Sierra to see if IFR conditions and/or mountain obscurations may be occurring or may be forecast to occur. This second statement reminds you severe or greater turbulence, severe icing, low-level wind shear, and IFR conditions may be associated with thunderstorms. These thunderstorm-related hazards will not be spelled out within the body of the area forecast. The third and final precautionary statement is that altitudes not shown as above mean sea level will be denoted by above ground level or as a ceiling. As you may remember, ceilings are by definition above ground level. In general, altitudes are MSL on area forecasts. Moving on to the synopsis, at 1900 Zulu, a cold front was positioned from western Lake Erie across southwestern Ohio through southwestern Kentucky. A warm front extended from southwestern Quebec through northern Vermont, curving through extreme southwestern Maine. By the end of the forecast period, which is 1300 Zulu, the low will be in southeastern Ontario, with a cold front extending through western New York, southwestern Pennsylvania, Beckley, West Virginia, Anderson, South Carolina, Tallahassee, Florida, and into the Gulf of Mexico. The first state detailed is Maine, and that is further divided into the northwestern 2/3 and the southeastern 1/3. In the northwestern 2/3, clouds are forecast broken to overcast at 2,000 to 3,000 feet mean sea level, with tops layered to flight level 250, which is about the same as 25,000 feet. The forecast calls for visibility 3 to 5 statute miles in mist. There should be widely scattered areas where the visibility will be 3 to 5 statute miles in light rain and mist. From 2000 to 2200 Zulu, skies are forecast to be overcast at 2,000 to 3,000 feet MSL. Occasionally there should be light rain and light drizzle. Occasionally means there's a greater than 50% probability, but it will occur for less than one-half the forecast period. Visibility during the period remains 3 to 5 statute miles with some form of precipitation and mist. The outlook calls for IFR conditions due to ceilings, rain, mist, and fog. The southeastern one-third of Maine is forecast to have overcast ceilings at 1,000 to 2,000 feet and tops of the clouds layered to flight level 250. Visibility should be 3 to 5 statute miles in light rain and drizzle. The outlook is also for IFR conditions due to ceilings, light rain, mist, and fog. For New Hampshire and Vermont, the northern half is forecast to have broken to overcast skies at 2,500 feet and tops layered to flight level 250. Occasionally, visibility should be 3 to 5 statute miles in light rain showers. From 0300 Zulu to 0500 Zulu, clouds should be overcast at 2,500 feet, and visibility of 3 to 5 statute miles in light rain showers. The outlook is for marginal VFR due to ceilings, rain showers, and mist. The southern half of New Hampshire and Vermont should have broken overcast clouds at 1,000 to 2,000 feet with tops layered to flight level 250, with visibilities from 3 to 5 statute miles in light drizzle and mist. The outlook is for IFR conditions due to ceilings, drizzle, mist, and fog. Let's read through one more. This one issued from San Francisco on the 12th of the month at 11:45 Zulu. The synopsis is valid through the 13th and 0600 Zulu. Clouds and weather are valid until the 13th at 0000 Zulu. The outlook is from then until 0600 Zulu. This area forecast covers Washington, Oregon, California, and the coastal waters. Following the standard precautionary statements is the synopsis, which calls for an upper ridge over the western United States moving slowly eastward, as an upper low over the Gulf of Alaska moves eastward, bringing a southwesterly flow aloft across the northern portions of the forecast area, with variable clouds and precipitation across western Washington, western Oregon, and northwestern California. An upper ridge is continuing over southern California through the period. We'll look at the clouds and weather section for Oregon, the Cascades, and westward. For the coastal sections, Willamette Valley and the northern Cascades, broken to scattered clouds at 2,000 feet and an overcast layer at 5,000 feet are expected. Cloud tops are layered to 15,000 feet with widely scattered light rain showers. Until 1800 Zulu, look for occasional visibilities of 3 to 5 statute miles in light rain showers and mist. The outlook is marginal VFR due to ceilings along the coastline and VFR for the remainder of the area. For the southwestern interior valleys and the southern Cascades, the forecast calls for scattered to broken clouds at 5,000 feet and broken clouds at 8 to 10,000 feet. Cloud tops should reach to 15,000 feet with isolated light rain showers. Until 1600 Zulu over the valleys, there should be occasional visibilities of 3 to 5 statute miles in mist, and the outlook is VFR. You can see from these examples area forecasts are not hard to read or understand. They are useful for long-range planning, but when it comes time to launch into the elements, you'll want more specific and timely reports and forecasts. That's where the METARs and TAFs we covered in the last volume come into play. You can obtain and contribute recent airborne information about cloud tops, icing, and turbulence using pilot reports. They are the only means of obtaining certain critical information for briefers and for forecasters. The letters UA identify pilot reports. UUA is used to identify urgent pilot reports. Pilot reports, or PIREPs as they are called, follow a standard format. Following the letters UA or UUA will be the location, time, altitude, aircraft type, and weather reported. Elements not reported are omitted from the report. The location given in a PIREP may be given in relation to a known geographic designation or on a certain radio at a given distance from a VOR. PIREPs of icing and turbulence will usually indicate the type of aircraft the pilot was flying at the time they made the report. The type of aircraft will give you an idea of the usefulness and validity of the report to you. Moderate turbulence reported by a Cessna 152 at 3,000 feet would not be of much use to a 747 captain. However, a 152 pilot should be very interested in moderate turbulence reported by a 747 crew at 3,000 feet. Here is an example of a pilot report over Boston at 1444 Zulu during a climb reported by a Boeing 727. Sky cover, base of the scattered clouds 2,300 feet MSL, base of the overcast 3,000 feet MSL, weather instrument meteorological conditions at 10,000 feet MSL. The letters FL are for indicated altitude. For airplanes at and above 18,000 feet MSL, it is the flight level. Here's an urgent pilot report from Great Falls, Montana, on the 180-degree radial of and 30 miles from the VOR at 1550 Zulu. At 10,000 to 11,000 feet MSL, a Cessna 310 reported freezing rain and light rime icing. Pilot reports of a non-meteorological nature sometimes help air traffic controllers. The following PIREP alerted pilots and controllers to a bird hazard. 3 miles north of Pensacola Regional, a large flock of goosey-looking birds heading generally north. Maybe seagulls, formation lousy, course erratic. PIREPs are an important part of the weather briefing. The most reliable observation of in-flight weather is the one made from the cockpit of an aircraft. PIREPs always help other pilots and become part of the Aviation Weather Service. Pilots are requested to please report anything observed that may be of concern to other pilots.
Let's take a closer look at what you might think of as beehive airports. A good example of a beehive airport is Vero Beach, Florida. It reminds you of a beehive that has bees buzzing all around, all trying to get into and out of the same place at the same time. By listening to the radio traffic, you can tell that the controllers and the pilots have to be on the ball.
Cherokee 9248 Hotel, Vero Beach Tower. Make left traffic, runway 11 left. Report the left downwind. Traffic's 2 helicopters and left close traffic. Unable to left base at this time.
Vero Tower, Cessna 66977.
Remember 66977, Vero Beach Tower.
4 miles south over the river at 1,600, like the transition through going north.
November 977, transition northbound approved. Vero Beach altimeter 3026. Report a bee in the Vero Beach Airport to the east and say your type aircraft.
152.
Cessna 977, roger. Aztec 77 Zulu, runway 11 right, taxi position and hold.
Position and hold, then Zulu.
Cherokee 36 Lima, turn right next intersection, contact ground off the runway.
36 Lima.
If you find yourself at a very busy airport, the basic rules of communication and airport patterns apply very strictly. Know what you want to say and be brief. Then listen. Fly your patterns where controllers and other pilots expect you to fly them. And have patience. The rules allow only one airplane on a runway at a time. It may take a while, but your turn will come. There's no reason you should avoid beehive airports such as Vero Beach. Just be prepared for what you're likely to find.
You and your instructor have checked the weather and filled out the flight log. After a thorough pre-flight inspection and getting the cockpit organized, you make the necessary radio calls before taking the runway, and you're off. After reaching pattern altitude on the departure leg, exit the pattern at a 45-degree angle. Then turn on course when clear of the airport vicinity and at least 500 feet above the pattern. After starting the timer in the E6B, the first job is to get established on course. So assume the initial heading of 50 degrees and begin looking for Owensville and the racetrack, your first checkpoint. There they are, which means you're on course. Log the time over the checkpoint and continue on course. Now that you are at the 3,000-foot cruising altitude, adjust the power to your cruise setting and lean the mixture. Double-check the conditions for determining true airspeed. A quick glance at the OAT gauge confirms that the outside air temperature is 1 degree Celsius, so the true airspeed calculations are valid. Remember to continue your scan. Don't get so caught up in flight management and duties in the cockpit that you forget to scan. The flight passes near several airports, which is extra incentive to remain vigilant. Log the time over the lakes. Do a ground speed check at the next checkpoint. Right after crossing the next road, you should see the town of Midland off to the left. There's the road, and there's Midland. The heading is holding the desired course, so your pre-flight information and planning must have been accurate. The ground speed check on the E6B is very close to the estimated 112 knots. The next checkpoint was a road and railroad together. Those are pretty easy to see. Our planned route takes us through the Wilmington Class D airspace. We must establish radio communications before entering the Class D, so we'll give Wilmington Tower a call.
Wilmington Tower, Skyhawk 810 Sierra Papa, about 6 miles south at 3,000 feet, heading northeast toward Fayette County. Request transition of your airspace. Skyhawk 810 Sierra Papa, transition approved.
There's the town of Wilmington on the left and Airborne Air Park just this side of it. Log the time by that fix, and you're on the final stretch to Washington Courthouse and Fayette County Airport. Off to the left is Sabina and the road leading to Washington Courthouse. Up ahead is Washington Courthouse, so prepare for approach and landing to Fayette County. A quick call to Fayette County Unicom on 122.8 is in order to get an airport advisory.
Fayette County Unicom, Skyhawk 810 Sierra Papa, about 8 miles to the southwest, inbound for landing. Request airport advisory, Fayette County.
Fayette County, active runway 4, Fayette County.
Fayette County's altitude is 982 feet, and the airport facility directory lists pattern altitude as 1,782 feet. The current altitude is 3,000 feet, and you're still about 7 miles away. Remember, plan to arrive at the pattern altitude before reaching the airport, so begin a descent in plenty of time. Don't forget the pre-landing checklist, and keep listening to the Unicom frequency for other traffic, and make your calls specifying what you're doing.
Fayette County traffic, Skyhawk 810 Sierra Papa is 2 miles to the southwest. We'll be entering an upwind for runway 4, Fayette County.
Once in the pattern, quickly log the time of arrival at the airport and concentrate on the landing. Keep scanning. Since you don't need a stop, a touch and go is in order.
Fayette County traffic, Skyhawk 810 Sierra Papa on the go, runway 4, Fayette County.
After reaching pattern altitude on the departure leg, exit the pattern at a 45-degree angle. Then turn on course when clear of the airport vicinity. Picking up the planned heading, the first checkpoint is the road and railroad track, which you should cross at an angle. What may be sinking in right about now is that you have successfully flown an airplane from point A to point B. The first leg of the trip seemed like it went pretty fast. That's because you were busy, without much time to sit back and reflect. The same is true now. So, back to work.
Coming up on the right is the lake, right where it's expected to be, so we're on course. Noting the times across the checkpoints, it sure does seem that they're not coming as quickly as before, which makes sense. We're flying into a headwind, so the ground speed is slower. A ground speed check shows that the ground speed is lower than planned, which means the wind speed must be greater than forecast. Looking at the OAT shows the temperature is also higher. That makes sense because the sun is warming things up. Recalculating true airspeed shows it's increased a little, but not much. Off to the right is the town of Xenia, the road leading there, and Greene County Airport to the west. Looking out the front, you can see the city of Dayton coming up. Since you'll use the Richmond VOR to track inbound to the Richmond Airport, go ahead and tune it in. You may be too far away yet to receive it, but at least get the station tuned in. Passing over I-75, Moraine Air Park is to the right. The VOR is now receiving a solid signal from the Richmond VOR, and the CDI centers on a course of 284 degrees to the station. Turning up the volume on the VOR nav radio and listening to the Morse code identifier further confirms a usable signal. The reciprocal is 104 degrees, which means you're slightly left of the planned 102-degree radial. Either the wind has blown you off course, or, in doing all this looking around, the heading has drifted a bit. By tuning in the Dayton VOR and getting a fix, the current position is approximately where the 104-degree radial from Richmond and the 180-degree radial from Dayton intersect, So out the front left, we should see the little town of Farmersville, a VFR checkpoint for calling Dayton Air Traffic Control. Recalculating ground speed based on this new position check indicates the winds are remaining pretty much constant. The private airstrip Morningstar North is there on the left. A little further on is the town of Eaton and the racetrack to the east. That means your position is about 10 miles out from Richmond Airport. The VOR indication is holding steady because you are right on course. A call to Richmond Unicom on 122.7 reveals that they're using runway 15 and winds are light. Richmond Airport has multiple runways, but identifying runway 15 is simple. You know that the runway number is aligned with magnetic direction. The fact that there's a compass rose on the chart around the VOR and that the VOR is on the field makes it that much easier. The runway running southeast-northwest is runway 1533. From our direction, we'll make a standard 45-degree entry to the downwind leg of the pattern. This will be a full-stop landing because a pit stop and something to drink are in order. At an airport with multiple runways, sometimes it's required to taxi across other runways going to the parking area. Even if they're not the active runways, always look and announce your intentions prior to moving onto any runway. At non-towered fields, you're on your own to exercise vigilance. At tower-controlled fields, permission is granted by ground or tower controllers to cross runways. After refreshing yourself and collecting your thoughts, off you go again on the final leg. Another pre-flight is a good idea, just in case something went awry during the flight. Exit from the Richmond pattern will be straight out from runway 15, on course back to Clermont County. On the way back to Clermont County Airport, navigate from the Richmond VOR on the 146-degree radial. Off to the right is the road paralleling our course, so you know we're pretty close to where we should be. The CDI indicates the desired course is left, so adjust heading about 5 degrees in that direction and wait for the needle to swing in towards the center. Off to the right is the large lake. Further south is the town of Oxford. Just beyond Oxford is the edge of the Cincinnati Class B airspace. At 3,000 feet, we're flying underneath the Class B, so no contact with ATC is required. The CDI is just about centered, so adjust your heading back to the original setting. There's the city of Hamilton and the Hamilton-Fairfield Airport. A ground speed check indicates the wind speed has increased again. You're making great time. You're halfway home and on course, so tune the ADF to the Sporty's NDB on frequency 245 and identify the station. As expected, the needle points dead ahead because you have a near direct tailwind. Remember, if we were compensating for a crosswind, the needle would not point straight ahead even if we were tracking straight toward the station because of the wind correction angle. After crossing I-75, there's Blue Ash Airport. A quick call to Clermont County Unicom tells you your crosswind skills will be needed. The tailwind that helps you get home is a crosswind for runway 22. Begin descending further away this time because your ground speed is higher. Looking ahead, there's the divided highway running just north of the airport. Approaching from the north-northwest to runway 22, enter mid-upwind on the 45-degree angle, announcing your pattern all the way to turning final.
What you probably realize by now is that flying cross-country is a lot of fun. And there's a lot to do to keep you busy. Just remember to keep scanning, follow the checklists, adhere to the procedures, and you should be fine. Everything went smoothly on this flight, but we'll find out in Volume 6 how to handle things when they don't go so smoothly.
Let's take a closer look at handheld flight computers. During our flight planning earlier in this volume, we used a Sporty's E6B. Whether you decide to get the regular E6B or the flat model, you'll find a handheld flight computer useful throughout your flying career. The Sporty's E6B is approved for use during the FAA Computerized Knowledge Test and can make it easy to answer calculation questions. Just plug in the numbers and the E6B does the rest. With its 3 built-in timers, you can easily determine ground speed, estimate your time en route, and keep track of Zulu time. Flight planning, including the all-important fuel required, is a simple process. The Sporty's E6B is lightweight and compact enough to be handled easily in the cockpit, and the flat model snaps right into standard chart binders. The display is easy to read at a glance, allowing you to continue your scan without distraction. With 19 aviation functions and 14 aviation conversions built in, you can see that Sporty's designed the electronic E6B with the pilot in mind.
Understanding the airspace system is easy once you grasp this concept. The designation of a parcel of airspace is driven by what goes on there. In the wide open spaces of the West, airplanes are so few and far between that we don't need many restrictions. On the other hand, we need more control around an airport where airliners are coming and going every 30 seconds. It's important that all pilots be familiar with the airspace designations and requirements for each one. As we go through them, look for the why of each class of airspace. U.S. airspace conforms to the International Civil Aviation Organization system. The International Civil Aviation Organization, commonly called ICAO, classifies airspace by the letters A through G, A being the most restrictive, G having the fewest constraints placed on it. In addition to A through G, there is also special use and other airspace. As we begin discussing airspace, there's one interesting note about these classifications. There's no Class F airspace in the United States. This is because the U.S. has no equivalent to ICAO Class F, where ATC provides separation for IFR aircraft only so far as practical. Now, let's begin with Class A airspace, which begins at 18,000 feet MSL and extends up to and including flight level 600. Remember, the flight levels are based on pressure altitudes, and pilots operating at and above 18,000 feet MSL must reset their altimeters to the standard pressure setting of 29.92. Flight level altitudes are expressed in hundreds of feet. For example, flight level 350 is a pressure altitude of 35,000 feet. All operations in Class A must be conducted under instrument flight rules, which is another way of saying that you can't fly at and above 18,000 feet MSL, VFR. You must be instrument rated and equipped, obtain an ATC clearance before entering Class A, and maintain two-way radio contact with ATC while operating in Class A. Class A covers all of the lower 48 states and the eastern section of Alaska. Class A airspace is not depicted on charts. The main users of Class A airspace are the airlines, the military, and business aircraft. They all tend to be fast movers, so ATC keeps a good handle on who's doing what up there and provides ample vertical and horizontal separation for all aircraft. Also watched closely is Class B airspace, located around airports where there's a large volume of air traffic. Class B airspace, often compared to an upside-down wedding cake in shape, begins at the surface and extends upward to a designated altitude. Aircraft inside Class B are permitted to maintain 250 knots indicated airspeed, the speed limit for operations below 10,000 feet MSL. However, aircraft operating below the overhanging layers of the Class B airspace are limited to 200 knots indicated airspeed. Before operating in Class B, you must receive authorization from ATC, maintain two-way radio communications with ATC, and have an operating transponder with altitude reporting. Private pilots may operate at all airports within Class B. Student pilots cannot take off, land, or fly solo in that airspace unless they have received ground and flight instruction for the specific Class B airspace. The student's logbook must have been endorsed within the previous 90 days by the instructor who gave the flight instruction. Recreational pilots working toward a private certificate may fly solo in Class B airspace after receiving an endorsement for ATC communication. At the busier Class B areas, such as Chicago and Los Angeles, student pilots may not take off or land at the primary airport. There are a couple of other special cases in these rules. First, an aircraft without a transponder may operate in Class B if the request for the deviation is made to ATC at least 1 hour prior to the proposed operation. Authorization to deviate from the altitude reporting requirement may be given immediately. The minimum VFR visibility in Class B is 3 statute miles, and you must stay clear of clouds. Class B airspace is shown on World Aeronautical, Terminal Area, and Sectional charts. Let's look at Houston as an example. Class B boundaries are shown with heavy blue lines. There are 4 layers in all. Let's begin in the middle and work our way out. The top of the airspace is 10,000 feet MSL, and in the vicinity of George Bush Intercontinental, it extends to the surface. The next layer starts at 2,000 feet MSL. The next layer at 3,000 feet MSL. And the outside layer begins at 4,000 feet MSL. Flying over or under the Class B area, and within 30 nautical miles of the primary airport, the aircraft must have an operating transponder and altitude reporting capability if the aircraft was certified with an engine-driven electrical system. You'll typically see lots of airline traffic in Class B airspace, usually heaviest around pushes, as a carrier lands or departs many of its planes close together. This is a result of the hub and spoke system the airlines use, and it's best to avoid Class B areas altogether around push time. The airlines are also referred to as scheduled carriers, and from these schedules you can know when a push is going to happen, or the tower at the primary airport will usually be happy to tell a pilot when it's best not to show up. Class C airspace surrounds airports handling a moderate volume of air traffic and resembles a 2-layer upside-down wedding cake in shape. To operate in Class C, you'll need to establish communications with ATC and hold at least a student pilot certificate. A transponder with altitude reporting is required within and above Class C airspace. For VFR flight, a minimum visibility of 3 statute miles is required, and you must remain 500 feet below, 1,000 feet above, and 2,000 feet away from clouds. You will find Class C airspace on Terminal Area, Sectional, and World Aeronautical charts. It's depicted by solid magenta circles. This is the Class C area surrounding the Fort Wayne International Airport. The first layer, called the inner circle, begins at the surface and extends to the top at 4,800 feet MSL. The inner circle has a radius of 5 nautical miles. The second layer has a radius of 10 nautical miles and has a base of 2,000 feet MSL. Traffic advisories are provided to all aircraft in Class C. In Class C and Class D, unless otherwise authorized, you may not exceed 200 knots indicated airspeed within 4 nautical miles of the primary airport at or below 2,500 feet AGL. Class D airspace surrounds tower-controlled airports that do not have an associated Class B or C area. Again, you must establish two-way radio communications with ATC before operating in Class D airspace, and you must possess a minimum of a student certificate. Class D airspace is depicted on VFR charts with a segmented blue line. Many have arrival extensions, giving the airspace the shape of a keyhole. The actual vertical boundary is charted inside a blue segmented box in hundreds of feet MSL. VFR traffic advisories from ATC are provided on a workload permitting basis. Some towers operate part-time, and when the tower is not in operation, Class D airspace reverts to the less restrictive Class E or G. Class E airspace is controlled airspace that is not included in Classes A, B, C, or D, and extends upward from the surface around some non-towered airports, or up from a floor of either 700 or 1,200 feet AGL in most other areas, up to, but not including, 18,000 feet MSL. Radio contact is not required to fly VFR in Class E airspace. Cloud clearances in Class E and below 10,000 feet MSL are 500 feet below, 1,000 feet above, and 2,000 feet horizontally from clouds. Below 10,000 feet MSL, 3 miles visibility is required. At and above 10,000 feet MSL and more than 1,200 feet AGL, this increases to 5 miles visibility and cloud clearances of 1,000 feet above and below, and 1 statute mile horizontally. To take off, land, or enter the traffic pattern of an airport in Class E airspace, you must have a minimum ceiling of 1,000 feet and a minimum visibility of 3 statute miles. One exception to this requirement is a special VFR clearance, which must be requested by the pilot. Special VFR allows VFR flight to and from airports in controlled airspace with a minimum visibility of 1 mile and still remaining clear of clouds. At just 90 knots ground speed, 1 mile visibility gives you little more than 30 seconds of forward visibility. Used wisely, Special VFR can help you cope with very localized conditions. Resist the temptation to fly Special VFR in unfamiliar territory or for more than a few miles. Paraphrasing Mark Twain, cowardice is the surest protection against temptations to risk life and limb. Special VFR at night is even more of a special case. Realizing this, the FAA requires an instrument rating to be cleared for Special VFR at night. No Special VFR is allowed inside the inner ring of airspace surrounding airports with the notation "No SVFR" above the airport name. In addition, the box around the airport name indicates coverage by FAR Part 93, covering special traffic rules and patterns. Class E airspace is depicted on VFR charts in various ways. Class E airspace having a floor of 700 feet AGL is encompassed within a magenta vignette. The airspace outside of these magenta vignettes is assumed to be Class E airspace with a floor of 1,200 feet AGL. When Class E airspace with a floor of 1,200 feet AGL abuts Class G airspace, it's charted with a blue vignette. This is most common in the western United States. These blue vignettes are framing a federal airway. Class E controlled airspace with a floor of 1,200 feet AGL along the airway and feathered side of the vignette, and uncontrolled Class G airspace on the sharp side of the vignette. Federal airways are designated routes between navigational facilities. This airway is Victor 121, the Victor identifying VORs as the navigational facilities defining the airway. In cases where the floor of Class E is other than 700 or 1,200 feet AGL, but less than 14,500 MSL, it's depicted by jagged blue lines, and the floor is marked in AGL, or in some areas, MSL altitudes, most often near airways or nav aids. Some of the Class D airport extensions are also designated full-time Class E airspace. These are depicted by magenta segmented lines. Some non-towered airports are surrounded by Class E airspace that goes all the way to the surface. These are also depicted by a segmented magenta line. Except where charted at a lower altitude, Class E airspace begins at 14,500 feet MSL and extends up to, but not including 18,000 feet MSL over the 48 contiguous states, the District of Columbia, Alaska, and coastal waters, not including the area west of 160 degrees west longitude or airspace less than 1,500 feet AGL. For the really high flyers, Class E begins again above flight level 600 with no upper limit. That brings us to Class G airspace, also referred to as uncontrolled airspace. Hark back to our previous discussion and remember that airports with magenta vignettes have a Class E floor of 700 feet AGL, which is also the ceiling of Class G. You'll find these airports also have an instrument approach procedure. The rules for operating in Class G are fairly simple. You don't have to talk to anybody or get permission to be there. You do need certain visibility and cloud clearances, though, which vary by altitude and whether it's day or night. We'll begin with visibility and start at the ground and work our way up. Below 10,000 feet MSL, visibility must be 1 mile. At night, this goes up to 3 miles. At or above 10,000 feet MSL and more than 1,200 feet AGL, day and night, this increases to 5 miles. Let's do the same thing for cloud clearances. 1,200 feet or less above the ground, you have to stay clear of clouds. Between 1,200 feet AGL and 9,999 feet MSL, you must remain 500 feet below, 1,000 feet above, and 2,000 feet horizontally from clouds. Above 1,200 feet AGL, and at or above 10,000 feet MSL, you must stay 1,000 feet below, 1,000 feet above, and 1 statute mile laterally from clouds. An airspace designation not included in the ICAO system is the Terminal Radar Service Area, commonly called a TRSA. TRSAs are depicted on VFR charts with gray rings. There are only a few TRSAs left. As the name implies, Radar Traffic Advisory Service from ATC is available near a terminal in a TRSA. However, whether you get this service or call ATC within the boundaries of the TRSA is up to you. You're very likely to find Class D or E airspace around the primary airport in a TRSA. Keep in mind that pilot adherence to the rules in these areas is not optional. Visibilities and cloud clearances will be those dictated by the class of airspace within which the TRSA is located. Up to this point, our airspace discussions have included weather, aircraft equipment, and pilot qualifications. Now we're going to talk about special use airspace, which establishes limitations on the use of the airspace itself. Special use airspace consists of prohibited, restricted, warning, military operation, alert, and controlled firing areas. All these, except controlled firing areas, are charted on terminal, sectional, and world aeronautical charts. Prohibited areas specifically prohibit aircraft flight, period. The prohibited area P56, for example, is in 2 parts over Washington, D.C. The tabulation of special use airspace on the chart defines the vertical extent of P56 to be up to 18,000 feet. It is in effect continuously. There is no air-to-ground communication, and an additional admonition is given to avoid this area. Restricted areas are defined as airspace where aircraft flight is subject to restrictions. Restricted Area 6612 is in effect to 7,000 feet Monday through Friday between 0800 and 1700 local time. At times other than those, R6612 can be activated with 48 hours notice. Therefore, pilots should check with the Washington Air Route Traffic Control Center whenever they plan to fly through this area. Warning areas are in international airspace. Activities in warning areas may be hazardous to non-participating aircraft. Warning areas cannot be designated restricted areas because they are over international waters. Warning Area W72B on the Washington sectional chart advises flight in the area is hazardous. Military Operation Areas, MOAs, are segments of airspace defined by vertical and lateral limits used to segregate military training activities from aircraft operating under instrument flight rules. Most military training requires abrupt flight maneuvering. In an MOA, military pilots are exempted from FAA regulations prohibiting acrobatics in certain airspace and on federal airways. MOAs identify areas where these activities are conducted. Pilots of VFR aircraft should contact any flight service station within 100 nautical miles of the MOA for real-time information about its current status. Alert areas are depicted on charts to warn pilots of a high volume of pilot training or other unusual aerial activity. All operations in an alert area are conducted according to federal aviation regulations. Pilots of participating and transit aircraft are equally responsible for collision avoidance. Alert Area A632E is established because of student jet training. Controlled firing areas have activities which, if not controlled, would be hazardous to non-participating aircraft. They are not charted because activities are suspended immediately when spotter aircraft, radar, or ground lookout positions indicate an aircraft might be approaching the area. Other airspace includes military training routes and airport advisory areas. An airport advisory area exists within 10 statute miles of an airport which does not have an operating control tower, but does have a flight service station. In this situation, the flight service station provides traffic advisories to arriving and departing aircraft. Communication with the FSS is recommended, but not required. The initials FSS in the airport information block on the chart indicates a flight service station is on the airport. Use of the service is by no means mandatory, but it's always a good idea to use whatever tools you have available to you. Military training routes are mutually developed by the FAA and the Department of Defense. They are generally established below 10,000 feet MSL for operations at speeds above 250 knots. Terminal and sectional charts show MTRs used under VFR as VR, and those flown under instrument flight rules as IR. Those MTRs with segments above 1,500 feet AGL are identified by a 3-digit number. MTRs flown entirely below 1,500 feet are identified by a 4-digit number. Pilots are not prohibited from flying in a military training route. However, pilots should be extremely vigilant when flying on, across, or near MTRs. You can check the status of an MTR by contacting a flight service station within 100 miles of the MTR. Temporary flight restrictions may be imposed to protect persons or property in the air and on the ground from an existing or imminent hazard on the surface. This is to provide a safe environment for disaster relief aircraft and prevent an unsafe congestion of sightseeing and other aircraft in the area.
Temporary flight restrictions and limitations are implemented in areas visited or traveled by the President, Vice President, or other public officials. Temporary flight restrictions in the proximity of spaceflight operations provide protection from hazards to pilots and spaceflight crews. Notification of temporary flight restrictions or limitations is made by NOTAMs. We've told you a lot about airspace. There's a lot to remember in preparing for the written and oral portions of the test, but more importantly, this is information you will use just about every time you fly.
There's but one reason for the multitude of airspace designations. Their purpose is to prevent conflicts between high-performance airplanes, usually airline or military, and airplanes that aren't quite so swift. When there is such a mix, the concept of see and avoid doesn't work quite as effectively. In a faster airplane, there's just not as much time to see and avoid. With that logic in mind, just consider where airliners, for example, are most likely to fly, and you can be sure to find some restrictions on the airspace there. Class B airspace surrounds the busiest airline airports. Transponders with Mode C altitude reporting are required above 10,000 feet because most high-performance airplanes fly above that level. These are not rules that were adapted haphazardly. Unfortunately, most came after a serious accident. We must learn from such. There was once a collision above 18,000 feet involving two airliners. One of them was flying IFR and one of them was flying VFR. The horse was out of the barn, but a rule requiring all aircraft above 18,000 feet to fly IFR closed the door. In the late 60s, there were 3 collisions between general aviation aircraft and airline aircraft near terminal airports. And soon after that, terminal control areas and airport radar service areas came into being. It's no secret that airspace requirements have brought more complexity to flying, but that is life. Driving a car is more complicated now than in the past, what with cloverleafs and bypasses. 20 years ago, if you compared a relatively simple electric typewriter with today's sophisticated word processing software, many would have held that the computer system was too complicated. It'll never sell. And the simple fact is that most of us have learned things that are far more complicated than the airspace system. Flying is like many other things. To make it safer and more useful to more people, it was necessary to increase regulations. There weren't many cars on the road before they decided that everybody had to drive on the right. And when they paved that sucker, they put a stripe down the middle. And if we're going to protect our access to the airspace, we really have to be responsible users. All it requires is knowledge of the airspace rules and adherence to rules regulating the use of the airspace, plus a good scan for other aircraft, and hopefully a Mode C transponder in every trainer to continuously give controllers information on position and altitude. You're lucky, too. The airspace system is today probably about as complex as it will get. You'll learn it early and thoroughly, and when you hear some old-timer grumbling about how complicated it has become, you can scratch your head and wonder what's wrong with him.
Here we are again at the end of another volume. You've passed another milestone. You're beginning to pilot your craft from place to place. As the old saying goes, if you don't learn something from each flight, you're not paying attention. In your logbook, under remarks, log what you've learned and the circumstances surrounding that lesson. So learn from each flight. Have fun. And until we meet again in Volume 6, I'm Rob Ryder. So long.